Тихо, вот так и должно быть. Да. Начинайте. Так, коллеги, ну что, мы начинаем? Начинайте. Dear college, let me open 20th International Conference Distributed Computer and Communication Network. The welcome speech will be presented by Director of the Institute of Control Science of Russia Academy of Science, Professor Novikov Dmitry Alexandrovich.
Thank you very much, Vladimir Mironovich.
Dmitry Alexandrovich.
Do you hear me? Вы меня слышите, Владимир Миронович?
Just a minute. Dmitry Alexandrovich, we wait you.
I'm
Dmitry
ready.
Alexandrovich, are you ready? Yes, if yes, please press the button and you can start.
I have pressed the button. Do you hear me? No sound.
Yes, yes.
You hear?
Так, ребят, можете помочь?
We can hear you perfect.
Oh, okay. Thank you very much. Somebody hears me. Okay. Dear colleagues and friends, it's my great honor and pleasure to congratulate you with the opening of the conference on distributed computer and communication networks. This year we hold this conference in an inconvenient and strange situation caused by the new coronavirus, but I'm sure that it will not stop the process of scientific research, the process of scientific communication, and the development of the science. Okay, the traditional organizers of these conferences are the Institute of Control Sciences of Russian Academy of Sciences, People's Friendship University of Russia, and National Research Tomsk State University. And as well as the Institute of Information and Communication Technologies of Bulgarian Academy of Science. Our Institute of Control Sciences, has always been and remains the largest research team in Russia in control, communication, and automation. The Institute conducts research at the new frontiers of science in a wide range of control and information programs, including complex multidisciplinary projects with fruitful cooperation with other domestic and foreign research teams. One of the important lines of research is the development of theoretical foundation and advanced telecommunication networks and practical implementation of large-scale projects of broadband wireless network design. In this regard, for many years, the Institute has organized the International Conference on Control, Computation, and Communication. The current conference will bring together researchers and developments from academia and industry and telecommunication networks, mathematical modeling methods of control and optimization of distributed systems. Despite pandemic restrictions in 2020, we received 180 submissions from about 300 participants from 26 countries. The global research spheres of the conference particularly is emphasized by the list of plenary speakers, which include leading experts in the field of theory and practice of telecommunications from Australia, USA, India, and Finland. Proceedings of the conference, just like of previous ones, are published in proceedings volumes which are indexed in the Russian Scientification Index, and selected extended papers are published in the lecture notes in computer science, which is indexed by Web of Science and Scopus. The organizers of the conference have made great efforts for the success of this prestigious international conference. I wish all the participants a successful and fruitful work, and in addition, I wish you good health and good luck. Thank you very much.
Thank you very much, Professor Moltchanov. The welcome speech will be presented by Director of the Institute AMC8 RUDN, Professor Samuilov Konstantin Evgenievich.
Thank you very much, Professor Vishnevsky. First of all, my congratulations to the Russian Academy of Science, to the Institute of Control and Communications, especially to academician Novikov. Thank you very much for your great efforts for organizing the conference and to bring us together in this, in your buildings and at your facilities. Of course, secondly, I congratulate Professor Vishnevsky. This year is very important for him. He is co-chair of the conference, and you and participants and colleagues should know that this year President of Russian Federation signed the decree, and we can congratulate Professor Vishnevsky with the honored scientists of the Russian Federation. That is the highest level of scientists in Russia. Thank you very much, Vladimir, and thank you very much for all your life in science and for your efforts. Secondly, of course, I send all congratulations from authorities of the University, People's Friendship University of Russia, from President of the University, Professor Filipov, and secondly, from Rector, new Rector of our University, Professor Yastrebov. And we continue our conferences together with our co-organizers. You can see these organizers and their banners on this slide. From 2016, if I remember, Rudin and the Russian Academy of Science are together in this conference. And the results, I think, are tremendous, let's say. Please change the slide. And this year is very important for the conference and for our country and all countries all over the world. Actually, from next year, we are opening a new epoch in the digitalization of the world, the epoch of the so-called 2030 networks. Because the epoch of the 5G networks is finished this year. You remember that the 3GPP project already approved basically the standards of these networks, and now we are going to the 2030 deadline. We don't know what will be then, but we know that our conference and our participants, our colleagues, our guests will make a significant contribution to the creation of this network, to research in this sphere. And here you can see all key phrases, key words, which we gathered during last years at our conference. Some statistics about the DCCN conference, please. Some statistics about our conference. Next. Yes. First of all, about the institutes of Russian Federations, both scientific research institutes and higher school. During last years, 32 institutes from Russian Federation took part in the conference. Actually, that is whole geographic of the Russian Federation from the border of the east to the border to the west. You can see it here. Second, there are exactly 31 countries all over the world. You can see the map which took part in our conference during last years. Actually, I consider, and that is of course my personal opinion, that this is not conference, that is a congress, actually congress, because so much countries we have in our conference, so much institutes and organizations all over the Russia. A few words about today's conference and the logistic of our conference. That is the first day for us, very important day, when we feel the influence of the pandemic of the coronavirus on our life. And we remember that telecommunications bring us together. That is due to our efforts. We provide to all people all over the world communications. And year by year, day by day, we will bring more and more help to people all over the world to provide them services. For instance, today, if we could connect 65 people in multimedia mode to our conference, I think the bandwidth of the network will be exhausted. So we have a great tasks and great problems for nearest 10 years, especially in so-called ubiquitous creation of ubiquitous networks. And we should also to provide to people, not only in Russia, but all over the world, good bandwidth and good services, good and very qualitative services. Next one, please. So now a few words about our agenda. Today we have a plenary day. You know that we have 5 plenary presenters and plenary talkers, and from co-chairs, for my friend Vladimir, thank you very much. And I enumerated personally, only first names. First to Professor Zaslavsky, second to Professor Moltchanov, then to Professor Krishnamoorthy, to Professor Nikitin, and to Professor Chakravarthy from different countries all over the world, from Australia to Finland. Please, thank you very much for your beforehand, for your plenary talks, which of course, yes, I remember about the United States, not only Australia, and we are laughing together with Vladimir. Yes, thank you very much. And we are waiting for very interesting plenary talks today. You know, the agenda is published. Everybody remember that in 15 minutes, the first talk by Professor Arkady Zaslavsky will be started. Arkady is already here. We see, please, maybe if you will have time, you can even start 5 minutes before. And from tomorrow, we are starting our regular sessions. You remember that we have 3 tracks. We have 3 tracks. The first track is on computer and communications networks. The second track, track B, is on modeling and distributed systems and networks. And the third one, track C, is regarding the distributed systems applications. We have a lot of presenters from all countries, from all former countries of former Soviet Union, from Europe especially, and from other countries all over the world. Please be very patient, because it's our first experience with distance mode of the conference, and I do hope that all participants will join the conference, will join sessions. One opportunity is very interesting for all of us. Actually, everybody have opportunity to be at the section in parallel. Yes, you can do that, and using the corresponding references at the website of the conference. So, what else? 2 days, full days, Tuesday and Wednesday. The Thursday will be only the first part. Before and after lunch, we will have break. It's a pity that we cannot to drink coffee together, but I do hope that in 10 years we can do that using 20-30 networks. And due to the efforts of our participants and guests and our sophisticated services, which we will prepare during our research in our institutions and universities. So that is my only few words. Yes, I feel that we are everybody here in this institute at the Profsoyuzная Street in Moscow. I do hope that next year we will see everybody personally here, and we will spend very good days in Moscow. The weather is very good, and I do hope that next year will be the same. So, Vladimir, thank you very much again. Yes, actually, you can open now the conference, and to give the floor to Professor Zaslavsky, please.
Thank you very much, Professor Samuilov. Let me give the floor to the Professor Zaslavsky from Deakin University, Australia. Please, Professor Zaslavsky.
Okay, good afternoon, everyone. It's a pleasure to give a talk on this conference. Unfortunately, it's a remote presentation. I wish I was in Moscow today, and I plan to come to Moscow, but because of pandemic, because of COVID, we have to do it remotely. So you can now see me. I'll share my screen and I'll start the presentation in a second. I'll be using the chat board to see if there are any questions for me, or if you would like me to speak slower. So I hope you can see the first slide. So the talk is about Internet of Things enabled situational and context awareness, and building systems that can predict perhaps future situations and future context, and perhaps even drive those situations to what could be an optimal situation that the system wants to reach. A few words about the university I'm from. So the university is one of 30 public universities in Australia. It's one of the largest ones with 45,000 students across many campuses. So you can see the map. It was established in 1974. It's one of the younger universities. And we have students from 130 countries. And our focus is on excellent research and excellent teaching. In fact, with the COVID, the university made a relatively smooth transition from class-based teaching to remote teaching because we already taught lots of units and lots of courses online. So here you can see the map of Victoria with 4 campuses of our university. So Melbourne, Geelong one, and Warrnambool one, and some pictures of our campuses. The outline of my talk, I'll be setting the scene for the research, presenting motivational scenarios, and perhaps some definitions so that we are all on the same page. Then I'll be talking about a European Horizon 2020 project called Biotop, building IoT open innovation ecosystem, within which we built our context awareness platform, and which inspired us to continue this work with Internet of Things ecosystems, or systems of systems. I'll spend a few minutes on talking about the context spaces theory, which is a metaphor for multidimensional representation of how we reason and represent context and how we can predict future situations by various techniques. I'll be talking about the platform we developed as part of the European project, Biotop. And then I'll present our vision of further extension of our platform towards context and situation prediction and proactive adaptation. So that's my plan, and hopefully I should fit in 45-50 minutes that have been allocated to me. So first, motivational scenario. Please let me know if there are any questions or comments, or the slides are shifting slowly. So is everything all right so far? Any problems? Any issues with slides?
Yes, Professor Zaslavsky. Thank you.
Okay, so all's good. Yeah, good. So many of you would know that every year we have bushfires. So bushfires is nature's way of rejuvenating. In Australia, we have eucalyptus, gum trees, and they have very oily leaves and then don't dissipate. So nature then gets rid of the waste, of the forest waste, by self-initiating fires. And on that map, you can see the fires that burned throughout Australia between December last year and January this year. We had almost 2 million hectares burned, and the smoke was felt in all the major cities in Australia, in Sydney, in Melbourne, in Adelaide, in Brisbane, in Perth, in Northern Territories. What happened is that during that bushfire, almost 1 billion of wild animals have perished. Kangaroos, koalas, other animals. And those panicking animals can't find safe escape routes. So they start panicking and they burn and they die in massive quantities. So the challenge that we asked ourselves, the question we asked ourselves, can we actually create safe escape routes for animals using IoT, using sensing, using actuation? And as we know, robotics, UAVs, land-based robots, they're actuating arm of Internet of Things systems. So here you can see a burned koala. Here you can see a kangaroo escaping a fire. So this is a motivational scenario for us to think about how can we predict future situations, spread of fire, direction of fire, fire burning, and then detect the presence of wild animals, and then using IoT actuation to create safe escape routes, virtual fences for animals, and herd them out of the danger zone. So that was a motivational scenario for us. So let me introduce a few definitions. So we talk about Internet of Things. So Internet of Things is a massively distributed system of nodes. It's a global network infrastructure with nodes that can self-configure, that can reason, that have intelligence, physical, virtual, identities, physical, virtual, physical attributes. The nodes or the things communicate using standard and interoperable communication protocols. And they blend seamlessly with the environment. They recede into the background, so we don't actually notice them. And some of the pictures that you can see here, for example, at the bottom, you can see a honeybee with a sensor on top of it. And there was a project at the University of Tasmania where they tried to analyze the behavior of honeybees, because the population of honeybees is declining. And if we don't stop the decline, then we may end up with no honey in our kitchens. So they, for example, put a number of sensors, nanosensors on those honeybees to study their behavior. Then you can look at kettles, everyday appliances, toasters, fridges, which have internet connectivity these days. And we can talk about Internet of Kettles, Internet of Coffee Machines, Internet of Fridges. So things which will surround us and that can do lots of services, lots of things. But of course, there are lots of challenges that we have to deal with. So IoT whole of system pyramid we represent as a physical layer with sensors, actuators, observations. Then from the physical layer, we go to a virtual layer, we go to clouds, we go to fog, we go to edge computing with machines. And then on top, we have users, services, applications. And the data comes from bottom up, and decisions, feedback loop, tasking of appliances with certain tasks are coming top down. So Internet of Things, if we look at the history of Internet is for people. So people are the users of the Internet. In the Internet of Things, this will be machines. Machines talking to machines and then processing enormous amounts of data and coming up with recommendations, decision support to human decision makers at the upper layer. I also wanted to talk about smart and proactive systems. So smart systems incorporate functions of sensing, actuation, and control in order to describe and analyze a situation and make decisions based on the available data. And when we talk about available data, context comes into consideration, because context is the data which is not available otherwise to an entity or to a system. And this is where we can process sensing data, and we can reason about that sensing data, use artificial intelligence techniques, use various formal methods to predict and adapt the system and system's behavior to something that we would like the system to achieve, its goals, its objectives. And also, most of the current systems are reactive systems. So they react to the current state of variables. And by the time they could make a decision or reach next state, the data could be outdated, could be obsolete. So we need to talk about proactive systems that can predict future situations and future context, relevant data, and adapt the system's behavior to that future situation, future context. So this is where the title of this talk is coming from. So crystal ball, can we predict something? Can we predict future situations? Can we predict future context? And if we can predict that and we can see what the optimal situation is we would like to reach, can we, with the help of actuation, can actually make it happen? So can we combine a crystal ball with a magic wand? And some of the answers that we are offering are promising and could be perhaps developed and taken further. So a few words about the European project Biotop. building IoT open innovation ecosystem for connected smart objects. The project finished last year. We were part of it, and the project had 22 partners from all over Europe. We were the only partner outside Europe. Of course, there was a Russian partner from St. Petersburg, ITMO University. And the vision of that system, of the internet ecosystem that we were building, was to accelerate IoT solutions through easy creation of systems, to create smart IoT systems that can learn from experience and can propose most appropriate actions, PROACT, as we call it, and compose systems from new or existing smart objects and platforms without programming, using drag and drop techniques, for instance. So without requiring users to learn programming languages or computer science methods. And we also wanted to establish an open ecosystem for companies to create new software for IoT systems and new platforms with minimal investment and maximum return on their investment. As I mentioned, we had 22 partners, and that explains the variety and number of possible use cases. So we had 3 cities as our partners: city of Helsinki, city of Brussels, and city of Lyon. We had also some companies among our partners, a large auto manufacturing company based in Germany, in Munich. This company has a W in its name, but it's not Volkswagen, so you could probably guess which company is that. We also had a number of universities, Aalto in Helsinki and University of Luxembourg, very active, small but research active university in Luxembourg, EPFL in Lausanne, some German universities, and others. And also we had Fraunhofer as one of our partners. So before I move into context awareness and situation awareness and situation prediction, wanted to again get on the same page with my audience. Of course, I'm used to seeing people I'm talking to, I'm presenting to, and judging by their reaction to understand whether the message gets across and whether there is understanding whether we are on the same page. Unfortunately, with this remote way of delivering talks, I cannot see that. So if you have any question, if you want to ask anything, please use the chat board, and I'm happy to watch it and answer questions. If there are any questions, I'll see if there are any questions. No questions so far. So what is context, and how context is different from data? So the entity has its data, it knows about its variables. Entity could be a car, could be a piece of software, could be a robot. So entity knows, for example, if we take an example of a vehicle, a car knows its speed. It knows the amount of battery charge if it's an electric vehicle, or amount of fuel in the tank. It knows perhaps even the experience of its driver. And based on that, it can probably facilitate with making certain decisions. But the car doesn't know about the traffic jams ahead. The car doesn't know about the destination availability if the driver is looking for parking. So this is what we provide. So we provide data which is external to an entity. And the definition, most widely used definition of context, is any information that can be characterizing situations of an entity. So context is interpreted data linked to entity, and situation entity is involved with. So in this example, you can see 3 situations the entity could be involved with, and the entities could have different goals, objectives, and different sets of context parameters. And there could be also an identified or unknown situation. So I'll give some more examples so that we are, again, following the conversation, the talk, and you can see where we're getting at. So what is context spaces? Context spaces I have been developing with my PhD students and colleagues since early 2000s. And context spaces, it's a metaphor for multidimensional space in which context is represented as dimensions. And the dimensions could be continuous or discrete. So for example, gender as a context attribute, male, female. If it is location, location could be three-dimensional, altitude, longitude, and latitude. Or if we can enumerate all locations, it could be just one dimension. So we've been inspired by control theory, by the state space model by Ogata. And we developed a number of mechanisms and engines and implementation of those theories to arrive at where we are now. So I'll be talking about some of those. I'll be talking about the extra, which is extended context spaces reasoning engine architecture. And I'll be talking about COAS, which is context as a service. It's a platform, IoT-based platform that can provide context as a service to any entity that wants it. So let me give you an example of what is context, how we view context. So let's see what happens here. So a person is walking, and the context of that entity is location, acceleration, heart rate. Another situation is person is running, and that situation may overlap with the walking situation because some people could walk fast, and for some people that could be a running pace. So for the running situation, we have context that is described by location, acceleration, heart rate, and also respiratory rate. Then we have a situation where the person is eating lunch and the person is stationary, so location doesn't change with time. Acceleration is not there, and heart rate is calm, which also indicates it's a stationary situation, and the time. And if the system reasons its time between 12 p.m. and 1 p.m., and usually during that time the person is eating lunch, then the system infers a situation that the person is eating lunch. And then there could be an unspecified situation, or a person is in a meeting, and the context attributes include location, light, projector activity, and time. And then we can reason about a person being a presenter, or an attendee, or a technical assistant. So this is an example of how we view context spaces and attributes, and at every time. So potentially behavior of an entity could be described by hundreds of attributes. But in order to make this computationally efficient, we reduce the search space, we reduce the number of context attributes on which we operate up to half a dozen or maybe a dozen of most important attributes. And we use here the rule 80-20, which means that 80% of all the activities could be described by 20% of attributes. So for reasoning in the context spaces, we use Bayesian reasoning, we use Dempster-Schaeffer theory, which assigns probabilities to events, expresses our ignorance of what may or may not happen. And context spaces is built on a number of those theories and methods, including fuzzy and other techniques. And we provide an approach to purposefully model and reason about the occurrences of situations with limited available information. So since we are dealing with multidimensional space, the multidimensional bubbles that represent situations or application spaces could have different cardinality. And we developed context spaces algebra that operates with those multidimensional bubbles. Subsumption, intersection, difference, and so on. And we use different reasoning concepts for operating on context spaces. So in this example, you can see three situations that could be overlapping using three dimensions. So a number of people, a noise level, and light level. And it could be a meeting, and could be expressed by different values of noise level, of number of people, and light level. Or it could be a presentation, or it could be a Friday gathering with lots of noise and lots of people walking around, and light level reasonably high, and number of people also reasonably high. One of the follow-ups to the context spaces theory, or what is based on context spaces theory, is extra. So it's enhanced context-based theory-based reasoning architecture, which helps us predict what may happen. And the goals, and we take into account distributed network and multi-agent nature of IoT systems in general. So the goals of Extra Engine to utilize any kind of situation formulas, whichever usable, whatever way is to represent it. Be able to compose context awareness engine out of reusable components so that we can reuse them, especially if we are dealing with software agents that operate on edge nodes with limited resources. We want to achieve distributed context awareness through context sharing, context reuse, repurposing. And we also want to incorporate context prediction and proactive adaptation in such a system. We also want to be able and recognize and discover situations at runtime. And there are a number of ways how this could be done using machine learning or having manually defined situations or automatically generated situations from knowledge bases, for example, using ontology. And we have a project where we demonstrated how we can generate all possible situations, relevant situations based on ontology or knowledge representation. So Extra is further extension of context spaces, and I'll be talking about Extra for a few more slides. Again, there are plenty of papers, book chapters, journal papers which talk about the work we did with context spaces, with context awareness and situation awareness. So with context prediction, you can here see the pervasive computing system or context aware system. And probably you would know that Internet of Things didn't come out of nowhere. The history comes from RFID and supply chain, but another roots of IoT is pervasive ubiquitous computing, distributed computing, mobile computing, communication networks, robotics, and many other disciplines of computer science and electrical engineering, which contributed to Internet of Things. So in this slide, you can see a architecture of a context-aware system, which senses the environment or gets sensor input depending on the application. Also could be user input based on observations or user preferences. Then this data is fused, low-level validation occurs, and we produce low-level context, which helps us build context awareness. Out of context awareness, we infer situations, and the system becomes situationally aware as well. If the system is situationally aware, and on the right hand, you can see the context prediction component of that system. So if we can predict context and future states and variables of a system at some future time, then we also may want to adapt the system's behavior using actuation. Context prediction field can be applied to any level of context. Can be low-level context prediction, can be high-level context prediction, could be situation prediction. So the prediction results influence adaptation, but also little attention has been paid to adaptation having feedback, so feedback loop to prediction as well. So we want to study that link between prediction and adaptation. So I won't be going into methods of context prediction. They're based on well-known techniques like sequence predictors, neural networks, Markov chains, Markov models, hidden Markov models, Bayesian networks, branch predictors, trajectory extrapolation, dynamic Bayesian networks, time series forecasting, Kalman filters, decision tree learning, and many, many other algorithms. So let me now talk about the context as a service, the vision, the platform, and then I can talk about how this platform works and also demonstrate a couple of use cases where which we developed under Biotop system, and where we demonstrate how the platform works and what it delivers. So context as a service enables global standardization and interworking among different context providers and consumers. So in our platform, we have two types of entities, context consumers and context providers. Context providers are those entities which provide data streams. For example, parking facility could be providing data stream about parking availability based on service level agreement SLA to our platform. And then we could have context consumers, could be a driver who is looking for parking, or perhaps context providers could be garbage bins in a smart city, and context consumer could be a person who is looking for a garbage bin to dump construction rubbish to that bin. So in our platform, we developed a number of components and engines, and a number of challenges need to be addressed in our platform. So how to express context queries? So how can a context consumer request a service from our platform, from our system? So we developed a language which is called CDKL, Context Definition and Query Language. The platform development consisted of a number of PhD projects as well as some research work. So there were 3 PhD students involved in developing the platform. And respectively, we had 3 major components, 3 major engines in that platform. So we also have to find a way of describing context services. We have to execute high-level context queries versus low-level queries. We also have to store, index, and cache contextual information. The power of IoT is in real-time management. So it is easy, well, I wouldn't say it's easy, to collect data, to put data into the cloud, and then apply data mining or machine learning techniques to learn about the patterns. But the power of IoT is in near real-time or real-time management of events and situations and entities which are involved. So, for example, with the motivation scenario which I mentioned about, we can predict fire. Another thing, this prediction can be proven true or not. It may happen or not. But if we sense a temperature sensor and humidity sensor, and we know that based on rapid rise in temperature, it could be fire. And if we have also a smoke sensor, which indicates there is smoke in the air, then we almost 100% confident that there is fire in the area. So, and then we need to make decisions in near real time, how to deal with such a situation. So what to do with that situation, how to react to that situation, what techniques, what methods we can bring to put the fire down. So, and that's why we have a separate storing, indexing, and caching mechanism for fast search and retrieval of data, of cache data, perhaps, to answer the context query. We also work with validation and analytics in our platform. And one of the major engines is a reasoning engine, which also is linked to situation monitoring engine. And I'll talk about that engine in a few minutes. And obviously prediction, we have a vision of prediction, and we have some results, and we are currently implementing the prediction, situation, context prediction, and proactive adaptation into our platform. So we may hear in the context of this, in the context of that. So what we did with our platform, we operationalize context awareness. So with our IT platform. So you may be familiar with OODA loop, observe, orient, decide, act. And our platform is somewhat similar to that OODA loop because we do sensing, observation, discovery of data and context. Then we validate, interpret, make sense of the data. We reason about the data. Then we infer situations and context from the data we validated. Then based on the data which we validated and we recognize as important, relevant, timely, We support decisions, and so based on taken decisions, we do proactive adaptation of a system. And based on those decisions, we actuate. And then we go back to our loop to learn how well we predicted and how well we actuated. So that's why this platform has been developed as part of the EU Horizon 2020 project BIOTAP, and uses data sources like IoT devices, sensor, social networks, semantic web, structured and semi-structured data, and it provides near real-time context and situation awareness. So in the next slide, I'll demonstrate how our platform works. So here you can see numbers, right? So you can see three major engines. The green box in the middle, context query engine, CQE. It's the major component of our platform, which takes queries written in CDQL, interprets those queries, and then orchestrates further actions and what needs to be done with those queries. On top, we have a green box, which is called context reasoning engine. And at the bottom, we have context storage management system, which works with data store in memory cache, logging, logs, and knowledge base. So we have also a security layer, which authenticates users, context consumers, context providers, checks authorization, collects lots of data for accounting and auditing purposes, and monitoring purposes. So on the right side of that architecture, you can see context consumers and context providers. So context consumers are those entities which request context. So let's take an example of a vehicle. A car driver is looking for a parking. Imagine hundreds of spectators, of fans driving towards a stadium for a football match, and they all want to park somewhere around the stadium, to walk to the stadium. In that case, we are helping those drivers with identifying possible parking spot. We predict whether the parking spot will be available by the time the driver arrives. And we try to make sure that not all drivers are coming to the same parking facility, to the same parking garage. But the availability and destinations are spread reasonably around the stadium based on the services. So with the step one, the consumer issues a query in CDQL to the platform. The step two checks credentials of the query. And based on credentials, then processes the query in the context query engine. Then context query engine parses the query and retrieves possible context service definitions from the context storage management system. And then in the step 5, it again optimizes for the best possible service based on a number of criteria. Then the data context is retrieved from providers, could be retrieved at real time, at runtime, as well as from the cache. Then in step 7, we infer reason about situations and context. In step 8, we monitor situations. Then in step 9, we do housekeeping, organizing data, deciding whether data should be kept in cache or discarded. Then in step 10, we do various operations. In step 9, aggregation. Step 10, context storage management. And then we provide the response to the query in step 11. And here you can see in step 6 that we can also call context providers in real time. For instance, if we are dealing with the parking scenario, we could be getting data stream from the parking facility with the read frequency every 5 minutes. When there is a need to park and there is a large number of customers streaming towards the facility, we want to increase the frequency of the sampling rate and call the parking facility every 30 seconds, for example. So we can do that based on SLA, service level agreement. Now a few words about situation monitoring engine. So situation monitoring engine, why do we need situation monitoring? And that's where prediction and also adaptation take place. So what happens is that when we deal with hundreds of potential context consumers, we monitor their situation until they reach their parking destination, park and stop there and start charging, because in the biotop we dealt with electric vehicles. So in this case, we monitor situations of those cars, and if, for example, there is a traffic jam or an accident that may affect how they're going to reach the parking destination, we notify the cars or the drivers or the systems on board the vehicle about context change and new situation that has occurred. And then we also recommend an updated itinerary routing to a vehicle through the backend server of the automaker. And I'll show an example, animated example how this happens. So here is an example of a change in a situation. So sensor ID 123, current location XY, and timestamp. And we need to match an event which comes from a car, from a vehicle, with the situation description. And the situation is used for a car park with attributes, distance, car location, destination location, less than 1 kilometer. So the user expresses preference to park less than 1 kilometer from destination. And destination is home of the driver. And the driver doesn't have a dedicated car park. So that's an example of how we describe a situation. And in this diagram, which is also in our paper, this is the context prediction engine that we are currently building and integrating with our platform. So it consists of 5 major components, which is context query engine, communications and security manager, context reasoning engine, context storage management system, and context prediction engine. So the context prediction engine consists in turn of a number of components. With prediction technique selector. So we use a toaster model where we select the best prediction technique out of a library at runtime. We deal with ontology manager, where we represent knowledge about the domain and situations and context. We do pre-processing of context in the context prediction engine. Then we have a context predictor component. Prediction evaluation, how well the prediction is done, and then we can learn from prediction so that with every cycle of prediction, we can improve on prediction. And then we also have an actuation manager, which suggests what actions need to be taken, how to proactively adapt systems behavior, and how to actuate the IoT system. So let me give you a couple of examples with Extra Engine. And the example we did with one of my PhD students, he carries a phone in his back pocket, and he makes a move as if he's about to sit. The phone predicts, the system on the phone predicts that the phone will be set on, and the phone could be potentially damaged. So it makes a noise, it predicts that it will be set on, and then it makes a noise to alert a user that the phone is in the back pocket, and the user should not rather sit on the phone in the back pocket. So we use 2 types of sensors, orientation sensor on the smartphone, on the Android, and the application Extra, by the way, was developed, heavyweight Extra on the server side, and lightweight Extra that can run on smartphone devices under Android operating system. So 2 sensors, we used orientation sensor and accelerometer sensor. The orientation sensors produce roll, yaw, and pitch, the orientation angles. So yaw is azimuth, pitch is up, down, tilt, and roll is angle of movement around the longer axis. And acceleration is measured in relative terms. So this is the data we get from the sensors. We pre-process the data to validate the information and get high-level context from low-level context, which are values and variables from the sensors. By the means of spatial geometry, we extract absolute acceleration. Then, on top of the high-level context, we infer a situation. And the phone, the situation of the user sitting on the phone has been defined manually before. So the situation can be inferred based on values. And then, and the situation awareness, let me show what happens with the situation awareness a bit in more details. So we have a reasoning engine, reasoning agent, sorry, with context state. The context state situation phone in the back pocket, and situation user is about to sit on the phone. Both of them are defined in terms of fuzzy situation inference, extension of context spaces approach. So then we reason about the probability of each of those situations occurring, and then notify collects the situation awareness data and issues a message to the adaptation block. So the adaptation block just rings or says, don't sit on me. So if we activate text to speech, TTS, then the phone can even say, don't sit on me. Google Assistant, imagine Google Assistant saying, don't sit on me, please. Adaptation block subscribes to notification of user is about to sit and phone in the back pocket situation expression. So if both situations are occurring, are triggered, then situation awareness block sends information about it to the adaptation block. And adaptation block then alerts the user to the possibility of potential phone damage. So extra situations could be defined manually, or situations could be learned from labeled data, and use machine learning and weakly supervised machine learning, or preferably unsupervised machine learning, to label and discover possible situations. So let me also talk about the prediction. So acting on predicted context. So we predict context, and then we want to act on it. We want to adapt. So as I mentioned before, we are moving from reactive systems to proactive systems. That means we predict context, and then we have to actuate. And actuation could be based on actuation policy, which is defined by the enterprise or by user. And then we have actuators, if it's robots or if it's a fish tank or something else where physical action could be done, or even virtual action, software-based action could be done, that's where we actuate. So when we adapt and are about to act, the link between action policy and context prediction is sometimes overlooked. So we want to do what-if analysis. So if we adapt that way, what will happen with prediction? Or if we adapt that way, what will happen with prediction? So the link is often overlooked, and we want to investigate that link in more details. So that's kind of using reinforcement learning for analyzing the link between context prediction and action policy. So that was use case number one, using Extra, Android-based lightweight reasoning engine and prediction engine. The second use case comes from Biotop system itself. Context-aware parking and charging for electric vehicles is a hot topic these days, given that the number of electric vehicles is increasing. And because the range of electric vehicles is not that great. So if you want to drive between two cities, you have to charge your battery a few times on the way. So there are a number of other challenges, but if a user wants to park somewhere in an electric vehicle, the user also may want to charge that vehicle at the same time. So COAS, our platform, context service platform running in the cloud, provides dependable, relevant, accurate, validated information to the electric vehicle. And we used and we worked with our industry partner to make their vehicles smarter, more agile, and context aware. So there are a number of benefits when we can save time and money for users who are looking for parking. It's calculated that sometimes people who are driving, looking for parking through multi-story facilities, garages, or through the streets, sometimes waste up to 30% of fuel. So if we can direct them directly to where there is parking and charging, imagine how much benefits the user can get. So let me now show the through the animation, and then I'll show you perhaps a video if it can work. Remotely. So I'll be slowly moving with animation, and hopefully the screen will be showing and you'll be able to follow the movements on the screen. So we have here a vehicle and a driver requests route and car park from a backend server. And for many cars, it's not the vehicle-based navigation system which provides the route. They usually rely on more up-to-date information from the backend server, from the company. Like in this case, BMW backend server, which gets a request from a driver for a parking destination. And the assumption is that the driver also needs a charging point. So then the backend server asks our platform COAS for destination car park, where the user can park, given destination location, given user preferences, whether the user wants to park undercover, whether the user could be a disabled and then needs to park in a disabled space, whether the user prefers wider spaces or is a small car and can park in a small parking spot. So COAS talks to context providers and asks them for more up-to-date context. For example, OBD on vehicle on-board vehicle base, Google Maps, police database for information about recent accidents, weather portal to understand whether there is rain coming, because the user may specify in preferences that if it's raining, then the user prefers to park undercover if the undercover parking costs more. So, and then we can also have access to a user's calendar to understand what are the requirements in terms of when the user has meeting and how much flexibility the user has in finding the proper parking. So we also can, the context providers can also request up-to-date real-time context from parking facilities. And real-time capacity, along with how quickly the parking facility is filling up, could be provided to context providers, who are then transfer this information to COAS. So they provide us with the data, and we convert the data into context. Then we suggest car parks to the backend server. Backend server develops a route for the car, and then with the route asks us another query. So now tell me the context of the route. So in this case, the COAS collects data from context providers about the route, and it can also get a notification that there was an accident on one of the streets that potentially the car could be routed through. So it aggregates, consolidates all the context, and provides now near real-time context to backend server. And backend server now sends the optimized route to the car. So the car starts moving, and while the car is moving, I'll let you wait for the animation to take place. And then while the car is moving, there is an accident a few hundred meters ahead. So if the car continues on the same street, it will be stuck in traffic, and then the user could be late for parking and a meeting. So what happens is that we get information about the accident, and that's where situation monitoring takes place. So we monitor the situation of that vehicle, and we realize that the accident can affect routing and destination. So that means we need to proactively adapt the routing and change the routing to something else so that the user can avoid getting stuck in traffic. So we send information, additional context to the backend server saying you have to alert the car to a traffic accident ahead. And then you have to propose a new route for the car. So the new route is proposed, the car moves, arrives at its destination with a slight delay, but within tolerance margins, and then starts parking and charging. So that's one example of the parking and charging that we did with our industry partner, and we did end-to-end testing. And I'm going to demonstrate this end-to-end testing in my next presentation. So car preconditioning is one of those services that luxury cars want to offer their customers. So if it's -30 outside, the user may want to get in a car which has a bit more comfortable temperature. So when the system computes the user, the driver, left the home, and it takes 10 minutes for the driver to reach the car, the system will automatically switch on the heater to warm up the car to a comfortable temperature of 17, 18 degrees or 15 degrees if the user has a warm jacket. So the data flow for the preconditioning scenario, the car sends a query as a context consumer to COAS. COAS gets information from external context providers, gets context updates, computes how much time is needed to warm up the car or cool down the car. If it's +40 outside, you don't want obviously to boil inside a hot car. So then we get context updates, and then we notify the car about actions. We proactively actuate. And in this example, you can see a query in CDKL. Unfortunately, I don't have time to go through all the operators. So we extensively work with vocabularies and ontologies. For instance, you might be familiar with the schema.org, which is a community semantic web resource, which has a description, semantic description of entities, of situations, of concepts, which we use in our query. So we select events, event location, driver, car, temp. These are variables and context variables which we collect. When time difference of the event, start date, current time, is somewhat within driving distance, and then the distance from the driver is not walking distance. And we need to identify a destination which is less than 500 meters away. So we try to answer a number of questions in that query. And then here is the animation of such a preconditioning scenario. So here you have a user who has been detected to walk towards the car because the user may have an app on a smartphone, and that smartphone notified COAS about the user moving, and that the user pace is, I don't know, a couple of steps a second, and the distance between the user and the car is about 50 or 60 meters, and we measure the temperature. So that's the user, and then meeting location is here. The user starts moving. We get location updates in the COAS, and then we also collect data from context providers. And we then calculate time which is sufficient for the user to get into car and the car to warm up or to cool down with air conditioning. Then we send a preconditioning signal to the backend server. And backend server sends a signal to car. And by the time the user gets in the car, the temperature is comfortable and the user can comfortably drive away. So that's an example in our query again. So let me move to a quick video, if it can show on the remote. I hope it can show if the bandwidth allows. So here you can see two of my PhD students and myself and our guest from Munich, who came specifically for end-to-end testing. And behind us is the i3, BMW i3 electric vehicle, the one which was used in the experiments, end-to-end testing, where we actually showed that we can activate air conditioning by calculating the time we need to get into the car. Yeah, I'm getting in the car and sitting in the back seat to record. Yeah, to record when the air conditioning will be switched on. Yeah, there has to be a little light, white light blinking once the air conditioning is switched on. And here it is. Here you can see the light comes on. So that concludes my talk. Thanks very much for your attention. I'm happy to take questions and answer those questions. So please let me know if you have any questions. So you can use chatbot or activate your mic and ask your question. I'll switch to a chatbot. So thanks very much again.
Thank you very much, Professor Zaslavsky, for very interesting message. Question, please. If you have any questions, please raise your hand.
Yeah,
No
or type your question in the chat board. I can't believe that you don't have questions.
No questions. Thank you very much.
Okay, thanks so much again. Thanks for inviting me, and it's a pleasure to give a talk in your conference.
Arkady,
if you remember, I was in your conference early enough, many years ago. Yeah. Okay, thank you.
Okay.
So I'll stop sharing the screen now, and the floor will be open to the next presenter.
Okay. Now I invite Professor Moltchanov from Tampere University, Finland.
Thank you very much. Well, the only thing is that I'm not in the presenter mode right now, but I'm ready to start sharing the slides and continue our talk for today. Okay, I have the slides right. Yeah. So I'm starting sharing the slides. Please tell me if you can clearly see those.
Yes, we can clearly see them. Thank you, Professor Moltchanov.
That is great. That is great. First of all, I would like to say thank you for inviting me to give a kind of a plenary talk in the conference. Actually, So my talk today is going to be about millimeter wave and terahertz access networks. Those two are kind of a huge buzzwords these days. Actually, they envision to be kind of a next step in the evolution of the cellular systems. Well, basically, 5G millimeter wave systems are quite close to us, just kind of around the corner. Terahertz systems are expected to be kind of a next giant step towards multi-gigabit access over the air interface. And well, today I would like to talk mainly regarding the performance assessment of such kind of systems, because as you are going to see, as we are going to progress through the presentation, these systems are going to be quite unique. They have very specific properties that we have never seen, have never met at lower frequencies, let's say at microwave, where let's say the LTE operates actually, and they need very specific methods to capture their performance and to estimate the capacity of such kind of systems. So I'm going to start with something most likely you've heard a lot about, actually 5G systems, the next evolution in cellular technologies. Well, in fact, as people around say that 5G systems, as compared, let's say, to 4G systems, cellular systems, are going to be kind of a principally new step. It's going to be more closer to a kind of revolution rather than the evolution of cellular systems. It's difficult to say whether we are going to witness this, basically, but we have all the signs that this may indeed be the truth. Well, basically, if we are going to speak about 5G systems in a broader scope, we have all the elements of the successful technology that could bring a kind of unprecedented level of performance to the end users. The changes that have been introduced by the standardization organizations like Achyutha and 3GPP have touched all basic fundamentals at the network side as well as at the air interface. Probably one of the fundamental improvements in 5G as compared to 4G systems are going to be kind of a drastic change to the control plane of the cellular system, basically, introducing kind of a ecosystem for on-the-fly service provisioning for applications having drastically different, sometimes contradictory performance requirements. This is going to be implemented using features like network function virtualization, software-defined networking, network slicing. So basically, one of the major advantages of 5G as compared to the previous generation is going to be huge flexibility on the network operator side, actually. So potentially we may experience kind of a cellular system that is going to be configured on the fly to provide virtual actually without running its own transport network, cellular transport network. Actually, you could become a kind of a network operator and provide the services over the air. Actually, the only thing you will need is your SIM card, which might also be kind of electronic. So a lot of changes at the network side, a lot of flexibility, but strangely, today we're going to be talking about a little bit different things. We're going to be talking about the second huge improvement, which happens to the air interface. We're going to be talking about a new radio technology. This is kind of a standard label for a kind of a new wireless interface for the users that is promising to offer multi-gigabit access for the users. Actually, the requirements is really huge, actually, as said by Achyutha. So it's going to be like 10 gigabits per second per access point, which is even nowadays seems like a kind of unrealistic and futuristic. But well, like already said, the technology is almost over in its standardization process. The only thing is that operators are a little bit slowly adopting this technology, but it happens with each and every technology that appears in the market. So we're going to mainly concentrate on this new radio technology, and more specifically at a very specific set of frequencies where it's expected to operate and actually realize its full potential, to the so-called millimeter wave frequencies. Millimeter wave is a kind of generic buzzword, I would say, for the lower set of extremely high frequency band, spanning the band from 30 gigahertz to 100 gigahertz. Actually, it's exactly the band that is going to fulfill those requirements set by I2R to achieve like 10 gigabits per second per base station, actually, at the air interface. But before we are going to go into these details, I would like to tell you a little bit from the theoretical perspective, actually, why we are even talking about such kind of higher frequency wave technology. First of all, as you may probably know, actually, higher frequencies is something that we want to avoid at any price. When talking about cellular access. The reason is quite straightforward. The higher the frequency, the higher the path loss, actually, and the lower the coverage of a single cell, actually. And the lower the coverage, the higher the expenses of network operators establishing such kind of infrastructure. So in a kind of a perfect ideal world, we would like to stay at the microwave frequencies. But unfortunately, all those microwave frequencies which are below, let's say, 6 gigahertz, they are almost all regulated, actually, and we don't really have a lot of bandwidth to satisfy those requirements put forward by I2R. If you're going to take a look at the kind of a classic Shannon expression for the rate achieved over the wireless channel, so you can see that there are two principal components. I'm not pretty sure whether you see my pointer or not. That would be nice to know. Yeah, hopefully you do, actually. Logically, the Shannon expression for the rate achieved at the air interface at any channel basically could be divided into two logical parts. The first one is basically the bandwidth. This is what I'm trying to highlight right now, actually, which is denoted by B in here. And the second part is logarithm. And what we have under the logarithm sign is 1 plus signal to interference plus noise ratio, basically. Well, what I would like to say is that when developing fourth generation LTE technology, researchers and standardization bodies mainly concentrated on the second part, actually, what is under logarithm sign in here, actually, which is basically called spectral efficiency, expressed in the number of bits that can be transferred per 1 hertz per 1 second, actually. And right now, with all those technologies that have been already implemented in LTE, we are operating quite close to the Shannon bound. Actually, well, definitely it's difficult to say exact number how close we are, but people are saying from, let's say, 80% to 95% in terms of performance, actually. And well, observing this part, you also can see another very interesting thing, consistent behavior of the logarithm curve, actually. When we are trying to improve what is under the logarithm sign in here, actually, we are not getting a lot of gains, actually, because of the nature of the logarithm function. And well, taking into account that at microwave frequencies, we have a kind of a very scarce resource, a radio resource left, actually. So the only thing for us, basically, is to increase the bandwidth at the air interface to fulfill those requirements put forward by 3GPP and I2R. So basically, we have no other ways. There is only one way to improve the rate at the access interfaces to put more bandwidth for such kind of systems, actually. And well, this bandwidth is available in the millimeter wave band, and it's also available a little bit higher in the terahertz band, specifically in the lower part of the terahertz band. So this is major trend in modern cellular systems, actually. Improve the bandwidth, improve the rate, and that's it. And try to not play much with spectral efficiency, because you are not gaining a lot of implementing kind of a new, more advanced schemes. So that is the case. So Well, basically, millimeter wave is what is given to us. Actually, it has a lot of unknown specifics, unknown features. Actually, that basically questions the utilization of such kind of radio frequency wave for communications. But this is something that we have to deal with because there is no other way around. A little bit about radio specifics and propagation specifics in particular in the millimeter wave frequency band. First of all, what we know for sure is that applying the well-known Freese propagation law, which is basically written in a kind of a compact linear form in here, is that increasing the frequency of operation actually, for example, going from microwave to millimeter wave, let's say from 1.9, which is a band for LTE, to let's say 28, which is frequency resource number 2 according to 3GPP for new radio technology, we increase the frequency approximately 10 times, and taking into account the power of 2 here, we increase the pass losses 100 times basically. So this is huge. If we are going to, let's say, compare the base station, LTE base station operating using a certain amount of emitted power, actually, if you are going to magically switch it to operate a millimeter wave band, actually, so basically the coverage is going to be decreased 100 times, which is, well, not something that we would like to live with in cellular system. Luckily, there is a way how to improve the coverage performance of such kind of systems, and it's mainly directed to utilization of massive antenna arrays at the base stations, utilizing the beamforming capabilities of forming the beam and concentrating all of the energy emitted from the base station towards the user. Actually, so inevitably, millimeter wave 5G and R systems, and as we are going to see in what follows, terahertz system as well, they are going to operate using highly directional links, actually. So here we are talking about directionality of 10 degrees and even less. If you are talking about terahertz systems, actually, to overcome the propagation loss, the directionality of 1 degree, even less is needed. Which is, from one hand side, this is kind of a good feature of modern and future communication systems, specifically wireless communication systems, simply because, well, we are getting rid of interference in quite an elegant way, actually. We are trying to combat the pass loss, actually, and the side effect is suppression of interference, which is a very nice thing. But as we are going to see in what follows, it also adds additional problems to system designers, actually. Such high directivity may require frequent beam alignment operations, actually, forcing us to utilize a little bit of time to for beam tracking instead of actual data transmission. Additional, very specific feature of millimeter wave band is the blockage of propagation passes between the base station and the users, not even by buildings, which was always the case even in microwave, actually, but even by very small objects like, let's say, human beings, which are always there in the environment, actually, and, well, if a certain human is in between you, let's say, trying to access the base station, actually, and the base station itself, well, the propagation path is blocked. This introduces additional attenuation of up to 30 decibels, which is basically very frequently the reason of, not really the reason, but makes the choice between having a kind of a good link and having no link at all to the base station. So this brings us to a very interesting observation. Such kind of systems are expected to provide extreme capacity at their interface. You could think about, well, let's say about 10, 20 gigabits per base station is a kind of a huge capacity that could really be a competitor to wired access to the internet, let's say. But at the same time, actually, it struggles in those environments where it's intended to bring the capacity to, actually. It struggles in environments with huge density of crowds, in shopping malls, let's say, in crowded squares, where there is a lot of traffic demands actually. So this one of the most striking feature of millimeter wave band and as well as terahertz band that may completely prohibit the utilization of this technology in real environments actually, and we have to find out kind of ways how to avoid it. And finally, there is one specific feature which is not really related to, meanwhile, the blockage of propagation paths by a human body is shown here in the illustration. I do really hope you see my pointer. Actually, here is a kind of a non-blocked situation, and then humans start to pass the link between the base station and the mobile terminal, actually, and as you see, the quality of the channel fades away quite quickly, actually results in a lot of variance, actually, and then when the link starts to be non-blocked again, actually it returns to the actual level. You see here in these experiments, meanwhile, these are actual measurements implemented at 60 gigahertz. The attenuation is around 20 decibels. So it's really huge. You can think about attenuating the signal 10,000 times in linear scale, which is extremely hard to deal with at the receiving end of a communication link. Well, finally, last thing that is really specific to such kind of 5G and R system and terahertz system is that those systems are targeting a very specific type of traffic. This is definitely not related to the usage of millimeter wave frequencies, but it's related to the bandwidth which is going to be available at the air interface. So such kind of systems are targeting bandwidth greedy, very often non-elastic applications, non-elastic in terms of the traffic, serving like 8K videos, virtual reality gaming, holographic telepresence, things like this actually, something that as well as futuristic as this millimeter wave 5G and R technologies actually, but something that is going to become a part of our lives quite soon, I would say within the next 10 years. Well, so what is a challenge basically for system designers in such kind of systems? The challenge basically is to somehow provide reliable connectivity over inherently non-reliable medium actually. And on top of those things, we've had in the past the microwave, let's say, the microwaves like fading, fast fading, slow fading, blockage by buildings. We have a kind of a extremely dynamic blockage environment where the human bodies around may quite frequently block the propagation path. So you could imagine the service provided by this technology without any kind of additional measures to improve the session continuity. As for example, you establish the session, you are watching quite excellent video, 8K actually, at your new Samsung or Apple phone, something like that, providing such kind of quality actually, and then you get interrupted just 5 seconds from the beginning of the video. Actually, well, you don't really have any kind of service for a couple of seconds, then it's back again actually, and it lasts for a couple of seconds more and then disappears once again. And this might be the case actually if we are not going to provide any kind of improvements for such kind of technology, the ways how to avoid such kind of frequent blockage situation, frequent loss of connectivity in such kind of systems. And in order for us to be able to come up with such kind of advanced mechanisms, what we need is basically we need new models and new methodologies for analyzing such kind of systems with these unique features that have never been experienced in the past at microwaves actually. So in what follows, we're going to be talking mainly about the ways how we can modify those existing approaches or add some kind of additional specifics actually to capture this dynamic blockage environment and to capture something which was not inherent for wireless system, to capture non-elastic traffic requirements. Actually, if I require a kind of a service at let's say 25 megabits per second, I have to get it. There is no other way. Actually, I cannot. My rate cannot really be reduced to, let's say, 10 megabits per second. Actually, otherwise it's going to end up with a number of annoying things, like a kind of a loss of quality of user experience. And on top of this, we have to do that for the systems having extremely high directionality, actually, and our potentially multipass environment where the beam could reach the receiver, our number of different passes bringing different amounts of energy to the actual receiver. So all these things are quite unique to the millimeter wave, actually. And if we are going to talk a little bit about the terahertz systems, actually, even one more step towards the multi-gigabit systems. So all these specifics are there, actually. We have to have a kind of a quite directional antenna radiation patterns at both transmit and receive sites, actually. We have multipass environment. On top of this, we have unique features which is brought by the terahertz systems, actually, like atmospheric absorption of electromagnetic radiation, which is quite abundant, specifically due to the water vapor, which is everywhere around us, and the water vapor molecules have their internal frequencies in the terahertz band. So when the electromagnetic radiation in terahertz propagates through the air, actually a lot of energy is just simply getting absorbed. From let's say the propagation perspective, the effect is quite interesting, actually. So if you're going to drop here the exponential term, and if we are going only to consider the first term here, so the first term is a kind of a conventional propagation model at microwave, which works for millimeter wave as well. But if we are talking about terahertz waves, actually, where we have additional term related to atmospheric absorption, we have to account for exponential decrease in the amount of energy brought to the receivers. And if you know, definitely you know, such kind of exponential term fades away quite quickly compared to the power function, actually. So the coverage of such kind of systems are going to be even more limited, and we have to use even more antenna elements to form the radiation patterns. That's why, as I mentioned previously, the directivity in terahertz band has to be less than 1 degree, actually. On top of this, for terahertz systems, we have some kind of additional specifics, like antenna misalignments caused by micromobility, which is briefly illustrated on the left-hand side of this slide, actually. So when we are doing something with our terminals, with our mobile equipment, actually, we don't really stand still. Actually, we rotate a little bit. The mobile terminal is also rotated on our hands, actually. So frequent beam misalignments that could happen at micro second scale, actually, is a kind of thing that may drastically affect the performance of the systems. But the net effect is, once again, a frequent loss of connectivity, just like we saw at the millimeter wave due to blockage. Here we have blockage, and on top of this we have a micromobility, and both these things actually results in the loss of connectivity quite frequently, which is a drastic difference compared to microwave systems. So what we could do to capture the performance of such kind of systems, and what kind of models are there available for us that we could build kind of a generic framework to assess the performance of such systems. Over the last 20 years, I would say, the performance analysis of wireless access technologies was solely done using the stochastic geometric approach. Well, basically, in other terms, geometric probabilities, basically. So the rationale behind this approach was that it's stochasticity of user locations around the base stations that mainly affect the quality of the channel. Indeed, the further we are from the base station, the lower the signal that we receive at the base station, actually, from that terminal. And the higher the amount of resources that need to be provided, actually, because the spectral efficiency decreases as we move away from the base station. So stochastic component was considered to be the most dominating factor for a third generation system and for fourth generation systems in the past. Well, a lot of quite interesting, quite comprehensive models have been developed, actually, but another side feature of the application of the stochastic geometry approaches is that the traffic at the area interface was almost always presumed to be elastic in nature. What it means? It means basically that the rate provided to the users actually depends on the channel conditions and depends on the number of users that are currently in the system. So in such kind of systems, we don't really expect any kind of losses, any kind of blockage of customers upon arrival. With customers here, we mean definitely imply session arrivals, basically. So all the users are accepted to the system actually and share the resource equally and possibly relative to its current received signal strengths, actually. But like already said, the things may change with the introduction of 5G systems. First of all, the environment, which is way more complex, actually, with those dynamic blockage conditions caused by human body blockage at millimeter wave frequencies, as well as human body blockage and micromobility at terahertz frequencies, actually results in the kind of service discontinuities at different times, actually. That has to be somehow taken into account, actually, and basically we would like to develop a model that model of those mechanisms that tries to get rid of such kind of unknown features of this interface. But on top of this, if you are going to take a look at the applications that are expected to run over such kind of technologies, as I already mentioned, they're kind of non-elastic in nature, actually. Like 8K video has to be 8K video, irrespective of your location with respect to the base station, actually. The millimeter wave could provide enough of capacity, but actually such kind of systems are going to be lossy in nature. You cannot really accept everything for the millimeter wave. And there is also one more limiting factor, which is related to the number of simultaneous connections that can be supported by the new radio. Because of the beamforming procedure, you are limited to 10-20 connections that could run concurrently in there. Otherwise, you are going to spend all your time on just beam steering procedures, actually. So taking all these things into account, actually, we see kind of a glimmer of hope for SGQ in theory that could be utilized at the air interface, actually, once again. The QN theory has never been applied in performance analysis of a wireless cellular system for a while, and this while is really long while, actually around 20 years, actually, since the emergence of GSM systems that was completely circuit switched in nature. Actually, the QN theory has never been utilized here, but right now we see that all the specifics of 5G millimeter wave access systems force us to use a kind of elements of QN theory, because simply we have to design the systems that doesn't really allow for a lot of sessions to be lost upon arrival to the system, actually, but at the same time we also somehow merge it with the stochastic geometry, because there are this stochastic factor still remains. The location of users still determines the quality of the channel and well, determines the amount of resources that has to be provisioned to sessions that requires a certain guaranteed bit rate at the air interface. So the idea, why not to marry these two approaches, actually, the stochastic geometry and QN theory. And one of the options to develop performance evaluation models for 5G millimeter wave and terahertz systems, actually suspected to the blockage and trying to carry non-elastic traffic is indeed to utilize these two elements at the same time, actually. Here, the stochastic geometry has to be responsible for capturing the specifics of the dynamic blockage phenomena of the directional antenna radiation patterns, actually basically implying that we create electromagnetic radiation only in one direction we want, actually, and emitting way less at the side and back lobes, actually. And we have to take into account the path loss specifics, actually, because it's quite different for blocked and non-blocked conditions. At the same time, from the queuing perspective point of view, we have a very specific queuing system, actually, that has to be able to deal with random resource requirements, which is drastically different from the conventional queuing theory, actually, where each and every customer that arrives to the system requires a certain line or a certain fixed set of resources. Right now, due to randomness and user locations, actually, each and every arrival to the system, each and every session, even though it may require exactly the same rate as any other session in the system, it requires random resources, actually. And such kind of systems are generally way more complex to analyze. On top of this, such kind of system has to capture additional specifics. For example, it has to capture potential state changes at the user equipment, actually. For example, capturing the transitions from the blocked to non-blocked conditions, and reallocating the resources appropriately, since in blocked conditions we have a much higher path loss. Actually, more resources has to be provided to maintain the same rate at the access interface. And well, finally, they have to be of finite capacity, definitely, because well, we are kind of deal with practical systems, actually, so finite amount of resources has to be assumed. Well, so development in this area is definitely needed. Development in stochastic geometry definitely needed. But the interface in between these two theories actually could be quite simple, actually. And this interface, for this interface, only 3 parameters need to be provided. The only thing is that, well, the procedure of providing these parameters is not really that simple, but we are going to discuss it, well, in the next couple of slides. We have to provide the coverage of a single base station, whether it's a new radio millimeter wave base station or terahertz base station. They have quite similar properties, actually, in terms of dynamic blockage and losses of connectivity. We have to provide the cumulative distribution function of resource requirements that has to be provisioned to an arriving session. And we also has to provide the intensity and duration of blockage periods. And then what follows, I'm going to briefly touch these equations, actually, because, well, the stochastic geometry has been quite well developed in the literature, and there is a lot of literature on quite recently, specifically from my colleagues from the Kettering University, analyzing resource-based queuing models with random resource requirements, actually. But marrying these two models, actually, the stochastic geometry and resource-based queuing system to provide a kind of a generic framework, generic methodology, how to analyze such kind of systems and analyze additional mechanisms, improving session continuity in 5GNR or terahertz, actually, is a kind of shaded area, I would say, up to some extent. So we are going to spend a bit of time on this. So how to utilize the stochastic geometry methods to parameterize the resource-based system, queuing systems. So this part of my discussion could be, I would say, treated as a kind of a mini tutorial or something like that, actually. But a little bit more is provided in publications that are attached to, that are summarized at one of the last slides in this presentation. Well, basically, we are concerned with Q parameterization, and as I mentioned, we have to derive 3 parameters, basically. The coverage of a single NR base station, or terahertz base station, actually, which defines how far how far from the base station users could appear requesting the service. The second parameter is a CDF, cumulative distribution function of resource requirements. And finally, the intensity of blockage and duration of blockage is a function of spatial density of users, not really users, but pedestrians in a certain area. In wireless systems, we always start with the signal to interference plus noise ratio, simply because this is kind of integral parameter that defines the quality of the channel and also provides a kind of a link between environmental characteristics, basically, and those 3 parameters I just mentioned. So the signal to interference plus noise ratio is shown here on the left, on the right upper corner. Actually, here you see kind of, as usual, I guess this expression is quite familiar to all of you. You have a kind of emitted power at the base station. You have a kind of antenna gain at the base station. You have antenna gain at the user, actually. All these parameters are basically constants if you are going to assume constant emitted power, actually. Antenna gains can be quite easily found using a kind of a very simple relation between the amount of antenna array elements and the gain expressed in dBIs. Actually, the only thing is that, well, this expression is in linear scale, so you have to change from the dBIs to the linear scale, which is quite simple. This is numerator, which is a constant in our particular case for a given system. What we have in the denominator, here is the situation is way more complex, actually. First of all, we have a kind of a thermal noise, which is, well, in our band of interest, it more or less constant at minus 174 dBm per hertz, actually. Well, in terahertz band, things are not really that simple, because after approximately 6 terahertz, actually, it starts to fade away and goes quite quickly to 0, actually. But most likely, the first terahertz communication system are going to be implemented in the lower terahertz band, spanning the frequency from approximately 275 to 325 gigahertz, something like that, actually. So it's going to be quite constant in such region of frequencies that we might be interested in the first generation of terahertz systems. Then we have a kind of a bandwidth in here, which is also constant, actually. Well, it depends on how many resources are currently provided to a certain user, actually. But if you know the amount of resources provisioned, then, well, it's basically a kind of constant, a certain number of resource blocks provided. Then the 3 quite critical parameters. The first is a pass loss, which is actually given and standardized by 3GPP in particular, with a model which is shown below, actually. So the pass loss in decibel could be expressed using this model, which could be taken right away from here, or you can browse the standardization documents, actually, for millimeter wave technologies. The same is available for terahertz as well, actually, which is quite constant. But the latter 2 components are kind of a shaded area here. First of all,
Professor Moltchanov, I'm sorry for interrupting you. Seems like there is some problem with the visibility of your presentation.
Really?
We can't see it anymore. Maybe you would turn it on again.
Yeah, I will
restart.
try.
Could you please restart showing the slides?
Yeah, I restarted it.
Yeah.
Can you see it?
Yes, now? Yes, now, yes, again. Thank you.
Well, when did you lose me?
Weiter. Next.
Okay, so a couple of minutes ago, right?
Yeah. Yes, thank you.
I see.
Thank you. Sorry for interrupting you.
Okay, I see. Yeah. So, well, anyway, we've discussed that the thermal noise is constant. The bandwidth is something that is known once the allocation is made at the base station. The propagation models has been standardized for both millimeter wave and terahertz propagation system. But the later two components, especially I here, the interference, is quite a complex characteristic actually. Well, the later one is so-called shadow fading, which is responsible for blockage by buildings and some other additional large objects in the channel. Actually, it's also standardized in non-blocked situation. It's around 3 decibels, in blocked situation around 8 decibels actually. But the component which is related to I is quite complex. This is interference. But before we go to the interference, I would say that taking a look at the path loss, which is shown in here, you see that there are two different expressions for the path loss in non-blocked situation and blocked situation. So when there is a kind of a human being blocking the propagation path, this branch has to be used. When there is no human being, this branch has to be used actually. So transferring everything into linear scale, actually, and substituting all these unknowns, actually, we end up with such kind of expression, where we have a kind of a constant from the numerator taken out of the brackets, actually, and inside we have the distance to the base station, which is random variable, actually. We have the blockage probability, which also depends on the distance to the base station, actually. And we have some additional components that account for interference, A1, A2 in here, and shadow fading as well. So almost everything is constant except for blockage probability and the distance to the base station. The blockage probability is something that can be easily found given a certain model of the environment of interest. Actually, for example, if we're talking about, let's say, kind of open areas like squares, I don't really know, large areas in the shopping malls, we could easily adopt a Poisson point process of blockers moving according to a certain random walk. In two-dimensional space, actually. Here we could utilize a very simple model from this publication, actually, where the blockage probability is given by a simple kind of a void probability of the Poisson process, which is just 1 minus the exponent at a certain power, actually. Well, the term in the power appears to be quite complex, but it's not, actually. It's basically the intensity of the blockers, which is lambda b in here, and the rest is the area of the so-called loss blockage zone, which I'm trying to point out right now. Actually, this is basically the area of the loss blockage zone, actually, and you see that the blockage probability is basically an exponential function of the intensity of blockers in the area and the distance to the base station, which is, like already mentioned, quite bad property for millimeter wave and terahertz systems. Having large capacities at their disposal, they're trying to target such crowd scenarios, but the blockage in these crowd scenarios is through the roof, which is going to place a kind of additional constraints on how to utilize this. In order to find interference, we could utilize another very interesting result, which is kind of a de facto approach utilized in stochastic geometry. Actually, here we could simply assume that the NR or terahertz base station follow kind of a Poisson process in two-dimensional space, which is very often the case. Actually, when talking about cellular networks, even from the term cellular, people are almost always presuming that the base station are distributed according to a kind of a regular structure, but it's no longer the case, actually. Even for LTE systems, actually, quite irregular deployments are utilized simply because of quite complex propagation conditions, specifically at city centers. But even in suburban areas, the situation is quite the same. And here, in order to assess the interference, we could estimate the interference at a randomly dropped point in such kind of Poisson process of base stations in here. And for to do this, we could utilize a well-known Campbell theorem that is known for years already, that tries to express the moments of certain functionals on the random fields. Actually, in our particular case, the expression for the mean interference is going to look as shown here in this expression. Actually, here PC is a probability that the receiver touches the transmitter touches the receiver with the interference. Actually, PB is a blockage probability, and FR is the propagation model that we defined previously. The only unknown here, we already evaluated the blockage probability. We already have a kind of a propagation model. The only unknown here is the so-called exposure probability, the probability that interferer touches the receiver with interference. Actually, for directional antennas at transmit or receive side, actually this probability is independent of the distance, actually, and simply given by the directionality of the main beam of the antenna divided by 2 pi. Actually, if directionality at transmit and receive antennas are simultaneously taken into account, this is just multiplication of two expressions like this, where alpha might be different depending on directionality utilized at the receiver. At the user equipment, usually its directionality is much weaker compared to the base station, something like this. If you would like to know a little bit more detail how to derive all this, actually, and to which expression this could be evaluated to, you could take a look at one of our publications, recent publications in here. Sometimes we could even evaluate this integral in a closed form, actually, given kind of a very simple expression for the interference in the random field of base stations, actually. Well, equipped with interference and the blockage, we could quite easily estimate right now the first parameter that we need is the coverage of a single base station. The only thing is that we have to be very careful in here, specifically taking into account that in blockage condition, actually, the coverage of a base station is much smaller compared to non-blockade conditions. And if you would like to develop a kind of system, to deploy a kind of system providing a kind of ubiquitous coverage of a certain area, actually, you have to dimension it with respect to the blocked situations, actually. So you just write in a kind of expression for the signal to interference ratio at the cell boundary and solve it with respect to the distance. Actually, it could be quite easy to do. Here is a term C2 refers to the coefficients related to the blocked situations. Once again, equipped with the signal to interference plus noise ratio, it's quite easy to find out the resource request distribution, which is shown below in here. Actually, here Fs is a distribution of signal to interference plus noise ratios that we've discussed previously, and epsilons here are simply the probabilities that a certain user is going to request this amount of resources, actually, depending on the signal to interference plus noise ratio distribution, actually. And the boundaries for 0, y, and up to the capital Y actually could be taken from the standard, let's say, FONR, physical channels and modulation, quite recently accepted in release 15. And for terahertz channel, you could find it in a little bit different standard, let's say, the only standard standard available for terahertz communication systems, standardized by IEEE 802.15.3D standardization group that developed the first ever standard for terahertz communication. There you could find the modulation coding schemes that provide the mapping between SINR and the amount of resource requested. And the only thing that is left for us to find is the intensity and duration of blockage situation. Basically, what we have to do is basically convert the spatial density of pedestrians, let's say. It's not only pedestrians, it could be cars, it could be people moving over bicycles, actually. It heavily depends on the environment of interest, but the simplest possible case, we could assume a kind of square, let's say, scenario where people are moving according to some kind of a random walk, actually. So we basically need to translate the spatial density of these pedestrians to temporal intensity of blockage events, actually, and also determine the amount of time a certain propagation path between the base stations, the user equipment is blocked. Well, the procedure is quite simple. This has been done, for example, in physics many times, actually. So we have a kind of a line of sight blockage zone associated with each and every user. And then we have a kind of a special process of pedestrians distributed in the landscape according to, let's say, Poisson model, actually, but you could take any other random model that you would prefer. Actually, the only thing is that results are much more complicated to derive for more complex models, like clustered models, let's say. And then you define a kind of a tiny boundary around the line of sight blockage zone, actually, and consider all the possible motions of users that falls into that tiny boundary, actually, that leads to crossing the line of sight blockage zone, actually. And one of the approaches how to translate this special density to temporal intensity of blockages in such kind of dynamic blockage conditions is basically highlighted in this paper, but the basic equation is provided in here. And one final thing, actually, is simply because in addition to the blockage intensity, you have to have also the blockage, non-blockage periods durations, actually, because these are those time-dependent characteristics that determines how long you may stay without an active link, actually. You have to determine this characteristic somehow, actually. So over the years, actually, of quite a kind of extensive research over the last 2 years, actually, researchers characterize this process as a kind of alternative renewal process with blocked and non-blocked intervals interchanging each other. In a very specific case of the Poisson process of blockage, blockers in the environment of pedestrians in the environment, the non-blocked time interval durations follow the exponential distribution. But, well, the blocked time interval durations follows a way more complicated model. Basically, it coincides with the distribution of busy period in MG infinity queuing systems as highlighted in this publication, actually. But you could always use kind of approximations for MG infinity, and you could go with MM infinity, for example, where the mean duration of blockage and non-blockage periods are given using quite simple expression, actually. For example, this expression for the mean busy period in MM infinity queuing system, actually, which, as I mentioned, coincides with blockage, mean blockage period duration, actually. The only unknown here you need to know is the mean amount, the mean length of the trajectory user spends when crossing the line of sight blockage zone. And this could be obtained using kind of conventional stochastic geometry approaches, actually. And, well, one of the models is presented in the paper I'm referring to here on the slides. Well, so that's basically complete that interface that I've mentioned to you about between the stochastic geometry and the queuing model with random resource requirements, actually. So the final formulas for effective cell radius, resource request density, blockage intensity, and blockage duration are provided in here, actually. And these expressions basically relates the environment and system parameters to the input that a queuing model has to accept, actually, in order to analyze performance of such kind of system and possibly propose kind of advanced techniques for blockage mitigation, actually, basically link loss mitigation techniques. Just a couple of words in the conclusion regarding the service process modeling at new radio base stations, actually, a little bit about the queuing theoretic models. Well, what is a major requirement here is that since the location of a user is distance dependent, actually, it creates a kind of a very specific situation when the resource requirements are random, even when the requested rate of application is exactly the same, actually. So the queuing system that we have to deal with has to have kind of random resource requirements. So instead of having a kind of a just arrival that requires a certain line, we have to have arrival that requires a certain amount of resources with a certain cumulative density function, actually. The rest is not that relevant. We could assume anything to the traffic arrivals, exponential service times, simply because, well, these two quite critical parameters for any kind of queuing system is not really that known for 5G NR and for terahertz systems, actually, because there are no statistical studies of such kind of arrival processes, actually. Well, the only additional critical thing is that you have to have a kind of external process of blockages associated with each and every customer which is currently in the system. With customer here we imply the sessions, actually. So the queuing system of interest is becoming kind of quite complex, actually. The arrival comes to the system, actually, a session comes to the system. It might be accepted or not accepted, depending on the current amount of utilized resources at the base station and the current amount of requested resources, actually. And then during the service time in such kind of system, it may change its state between blocked and non-blocked, and each state is associated with different amount of resources requested from the system, actually. So this constitutes quite a complex class of queuing models, actually. But luckily, such kind of set of queuing models have received considerable attention from the past, actually. There are a number of quite specific problems you have to deal with to analyze such kind of systems. One of those is related to keeping track of the amount of requested resources by all the sessions that arrive to the system, actually. So it naturally requires full description of the system, naturally requires n-dimensional Markov process, actually, which is impossible to deal with when trying to get any kind of results. So instead of keeping track of all the amount of resources requested by all the sessions that arrive to the system, we could utilize the state aggregation procedure, actually, and use the Bayesian procedure in order to estimate the amount of resources upon successful service completions, actually. So, well, but the theory, luckily, the theory of such kind of queuing system has received considerable attention in the past, and what one could apply any of those systems, well, with some kind of extensions, definitely that is specific for millimeter wave and terahertz communication system to estimate metrics of interest, which are quite important for system dimensioning. In addition to utilization and session drop upon arrival, arrival, kind of blockage upon arrival, actually. We have one more very interesting metric I would emphasize your attention to, actually. This is drop of session during the service, actually, because this simply could happen when the amount of resources that is requested or re-requested by the session which is already in the service is higher than the amount of resources available in the system, actually. In this case, this session has to be naturally dropped because the traffic is non-elastic. And this is in drastic contrast to 4G systems where, in this case, the amount of resources provided to this session could be just reduced by a certain amount. That is the case. So if you would like to get a little bit more information regarding the application of such kind of system and their variants, this is a kind of brief account of our recent publications on this topic, so you could take a look at those if you want, or otherwise you can always drop a message to me if you are interested in getting some kind of additional details. Well, I see I'm quite close to the time limit. Actually, I had a kind of a little bit of applications, but unfortunately, I guess I have to go to the end of the presentation. Here, a kind of application of the proposed methodology to improving session continuity in 5G and R systems, actually, and a couple of results have been presented here. But anyway, I would say we could easily skip those because those are also provided in publications, actually, and getting close to the conclusions. And one of the most interesting conclusions, at least in my opinion, is that the queuing theory with introduction of 5G and R millimeter wave and terahertz and new applications that are going to utilize resources of such kind of access systems, the good thing for all of us is that the queuing theory is becoming relevant again, actually, because it has been completely unutilized for a wireless access system for the last 20 years, actually, and all the network dimension has been made as human kind of elastic traffic using purely stochastic geometry approaches. Right now, when we are talking about non-elastic traffic conditions, actually, and on top of this additional complicating factors like the dynamic blockage environment, we have to go with the queuing theory, actually, to estimate and to properly dimension such kind of access systems. The methodology that has been partially presented in here could be extended in many different ways. Actually, we could extend one could extend it to resource reservation functionality at base stations. For example, you may not allow access to all the set of resources for a new sessions, actually, and the fraction of resources could be reserved for sessions that are changing state from non-blocked to blocked, such that they have some kind of surplus of resources to utilize without any kind of drops. You could model the case of very advanced capabilities like multi-connectivity operation when, in addition to a single link, links to multiple base stations in the close proximity are supported. Multiple flows, priorities, like already set applications for in 6G, because in terahertz communication system, because aside from kind of additional reason for losing connection due to micromobility, there are no other specifics from the point of view of performance evaluation modeling. And definitely there is a kind of a new wave of queuing models needed, actually, possibly complicating the arrival processes, priorities, locations, actually, all for queuing systems with random resource requirements and service interruptions during the service. And that basically concludes my talk. Actually, if you do have any questions, I'll be glad to answer those.
Hello.
Hello?
Konstantin Samuilov, can I put a question?
Yeah, sure.
Okay. First, Dmitri, thank you very much for a brilliant talk. We have not so much time. Nevertheless, we know that next week you must, I underline must, defend your doctoral degree in St. Petersburg. So you have candidate of science degree from Russia, PhD degree in telecommunications from Finland, and next week I'm sure you will have a doctoral degree from Russia again. So you know past, you implement present. And what about future? You understand 2025 epoch. And what about 2030? What are your feelings from every point of view? Please, from the point of view of end users, of technology point of view, maybe society and so on. Please, a few words about specific feature of networks 2030, your feelings. Thank you.
Yeah, that is a great question, actually. Because if one is going to take a look at all this evolution from, let's say, from the research and standardization community, so networks are becoming way more dynamic, actually. Way more dynamic and way more heterogeneous, actually. Not really a couple of years ago, a couple of decades ago, there was a kind of a concept of always best connected, actually. So this is something that perhaps our society is going to witness from the point of view of the connectivity in such kind of systems. There will be a kind of technology for any specific needs, providing the best service at the best time at the right price, actually. But this is a kind of a dream for telecommunications community. Network operators are way more stale, not really stale, but I would say way more, how to say, they're not really open to those changes, actually. Just a couple of words regarding, for example, 5G NR, actually. Well, at least in US, they're not really implementing such kind of technology within the next 5 years, actually. What is currently available in the market is not really millimeter wave NR, it's just microwave sub-6 gigahertz systems, actually. And at least what people are claiming, actually, the CEO of Verizon in particular, actually, he just recently claimed that we are not going to start with millimeter wave until the year 2025, actually. So maybe the year 2030 is going to be when we are going to see, let's say, a millimeter wave broadband access promising kind of new applications to their interface. So in my opinion, we are a little bit ahead in the research and standardization world. That is the case. But this is really personal opinion.
Sorry. I will have resources in 10 years to listen to your talk at some conferences after 10 years.
Yes.
Another question, please.
Can I put question?
Professor Vytovtsev.
Yeah, sure.
Professor Vytovtsev, Astrakhan. I would like to ask you about antenna arrays in terahertz domain. As I know, for today there are no any technologies for production of this antenna. How do you want to solve this problem?
Well, this is excellent question, actually, because well, there are a lot of specific related to the implementation of these antennas, actually. But well, luckily, I'm not a part of that community. Well, for us in telecom world, in networking world, actually, we just assume for granted they do exist, and they will do exist within the next. They will become reality within the next 5-10 years, something like this. There are already prototypes featuring steerable antennas having like up to 1,000 of elements, at least what has been reported by different research groups. But definitely they are not really produced at the kind of larger scale. They are still prototypes, but well, I'm sure the time will come and they are going to be a reality.
Okay, and I have a second question. Can I put?
Yeah, sure.
About antennas. You say about high directional antennas. How do you intend to solve the problem of position location in this case?
The problem of location?
Yes, location.
perhaps I didn't fully understand this question. Actually, definitely high directional antennas are going to be used. The problem of locating users is going to be solved using the beam tracking mechanisms, actually, where both the user equipment and base station are going to implement a certain algorithm to find each other out. Usually it's implemented by putting one of the sides in omnidirectional modes and another side into directional mode, and then the roles are inverted actually, and doing this way we find out the direction to the user, actually, where we could beamform our antenna. At least this is what they claim in the standards, actually. The only thing is that the actual beam steering and beam tracking procedure is left to vendors to implement. So most likely we're going to have plenty of proprietary technologies how to beam track faster than my competitor or something like that.
Another questions? No questions. Thank you very much, Professor Moltchanov.
Thank you very much for inviting me for this talk. And if any of the audience have further questions, I guess you have my contacts. You can drop me a message.
Okay. Thanks. Now I give the floor to the Professor Krishnamoorthy from SMS College, Kottayam, India. Да.
Yeah. Sit here. Are you able to hear me? Hello?
Yes.
Oh, okay. So I can start. So thank you, Professor Zaslavsky, Professor Dmitri, and all members of the organizing team in Moscow and Russia in general for this, for giving me an opportunity to share my thoughts with all of you. I should also thank Dr. Joshua, the principal of CMS College, Mr. Mithun, the web administrator, and his colleague Anish for providing me such a nice facility on the campus of the college for me to make the presentation. And also, I should say a few words about Professor Pavel and Professor Marcel F. Newt for introducing the very novel phase-type distribution. It's based on a Semi-Markov process, but within, not between two phase-type distributions. I will come to such details a bit later. So, to start with, I will go to the first slide, second slide. Now, long ago, more than 45 years ago, Professor Thomas L. Satie, he lamented, it appears research in gene theory has come to a dead end. It would have happened had these two great luminaries, Professor Bachorov and Professor Marcel Newt, had not introduced such novel idea. The presentation that I make will essentially involve the phase-type distribution, the Markovian array process, and its extension. To start with, I should go to preliminaries, but before that, let me admit frankly an important fact. Until 2 weeks ago, I was under the impression that the type of work that I am going to present was not discussed in the literature earlier. I searched, but I could not find anything. Until 2 weeks ago, I came across a paper by Adan and Kulkarni. And subsequently, from that to some other papers. That happened only a week ago. So something related to this has already been done, but we have still a lot to do. So with that, anticipatory bail, I proceed further. Now a bit of preliminaries is needed. Now we have the exponential distribution. It has the lack of memory property, which is in fact indeed a very nice property. But when you go to mixtures of exponentials, unless you specify which among the mixtures is in action, we will not be able to get this lack of memory property. When you go for commuting two exponential random variables, independent and identically distributed, that means taking the sum, not exactly commuting, taking the sum. Again, we are losing the lack of memory property. But if we specify which of these exponentials is in action, so then we call them stages. Then we get the lack of memory property. So the dimension will be increasing accordingly. So Erlang of k would mean that it is a sum of k IID exponential random variables. And it is always a forward movement. That means starting from when a queuing theorist analyzes it, Erlang arrival process would mean that starts at stage k, then staying there exponentially distributed time, it comes to stage k minus 1 and proceeds to stage 1 and then gets into the system. So that is the information additionally we require. In addition to what is the number of customers in the system, what is stage of the arrival of the customer in the arrival process. Similarly, if it is a service process, we label them in the reverse order, 1, 2, 3, etc. So a customer is in stage I means that he has completed service up to the I-1 stage in a forward direction, then coming to k and then completing the service there, he goes out of the system. So the number reduces by 1, whereas the number of stages has reduced by k by his leaving the system. Whereas in the arrival process, by the arrival of a customer, if it is according to Erlang of order k, k stages are added to the system when the service time is Erlang of order k, or whatever be that order. Then we can go to generalized Erlang, where the parameters need not be the same. They are independent exponential random variables, sum of independent exponential random variables, but not identically distributed. From that, one can move to Coxian distribution of order k, where the first one is always compulsory in the sense that a customer with a Coxian distribution of order k as his service time will undergo invariably service in first stage. Thereafter, it is like optional. He can quit after service in the first stage, or move to second, or jump certain stages, go to some other stage, and then keep on doing that until he finally gets out. But then, remember that the number of stages of service this customer gets will be a random variable subject to a maximum of k. Then we have, so what happens is in all these things, it is all forward movement, not in the backward direction. So what Professor Marcel Newts and Professor Buchero did, they thought of a system where, in addition to forward movement, you can also think about movement in the reverse direction until absorption takes place. So they introduced that they called the phase tape distribution. So for which you have a Markov chain of order m+1. If you label the states of the process as 1 to m, then m+1, with the first m stage as transient and m+1 the stage absorbing, then we get the phase tape distribution, time until absorption. That random variable is phase distributed. So this is the first stage of generalizing the Coxian distribution. Then comes the map, MMAP, of order, whatever order, integer order, positive integer order. Then we have BMAP. So along of order k, this is how the service arrival process would mean that from k, k-1, so on. Stage 1 and then getting into the system. Along service, just the reverse order. In Cox, as I indicated earlier, it is first one that is compulsory, remaining, well, it is optional. And then time until absorption, that is the Coxian distribution. Now, for the phase tape distribution, so we have a Markov chain on a finite state space. 1 to m+1, m+1 is absorbing. 1 to m, they are transient states. And then an object moves for a customer. For example, a customer is undergoing service. He starts his service in some stage, transient state, and then keeps on just going around the transient states with the sojourn time in each state exponentially distributed with parameter. Well, the exponential random variable, the sojourn time random variable is Tij. Why there are two suffix? That is because I is the state in which the customer is in service. J is the state to which it is going to move according to the one-step transition probability matrix of the Markov chain. So Tij is exponentially distributed now with parameter depending on both the state in which it is in and the state to be visited next. So exponential Rij, that is the distribution of a Tij. Now suppose it moves from I to j then to k with I and j both different from m+1. That means not absorbing states. Then what happens is, so after sojourn time Tij, spending Tij amount of time in state I, the customer moves to state j, and the time it spends, which is Tij, has exponential distribution with this as parameter R sub ij. From j to k, again j it is going to stay for an exponentially distributed amount of time with parameter, because it is going to state k, because that is the one that is chosen according to the Markov chain rule. So Tjk is a sojourn time random variable in state j. This is exponentially distributed with parameter R sub jk. Now notice that the suffix of the Rij, so second suffix j here and the first suffix in Rjk, they are the same, j. Therefore, naturally a correlation between the random variables Tij and Tjk comes into play. But being exponential, well, there are so many other interpretations coming there. Now, therefore, I can say that these two random variables Tij and Tjk are correlated. Then what happens? The sojourn time random variable within the transient states designated by, I just wrote it as T, but the T I should not have written because for representation I again used the same T. Anyway, so if T is the total amount of time that is spent by the customer for service in the system, that means in the transient states before getting absorbed into M+1, then what happens? T is the random sum of a random number of exponentially distributed random variables. This random number of random variables, number can be arbitrarily large, with the result that the mean time until absorption may go to infinity, which means that the matrix, the transition rate, that matrix on the part of the transient states can be non-invertible. That will be giving the consequence the mean turns out to be infinity. Otherwise, it is finite mean, and then so much computations can be made. Otherwise, what happens is it is something like a terminating process. So now what happens? If you take the pH distribution, I take a pH renewal process. The consecutive, if I take a pH renewal process, now suppose I take successive inter-occurrence times. So initially at time 0, well, nothing has happened. So now we are starting here. So there is an initial probability vector alpha bar, and instead of T, I will write U here. This is the infinitesimal generator of the transient part. So rho sum cannot be expected to be naturally 0. It's not. Then this is the time at which the first event occurs. Now here, whatever happens, so number of transitions among the transient states according to a semi-Markov process. So within there is correlation, within the phase state process. Once the event realizes, the next event to start will have its initial state sampled out from this initial probability vector. It has nothing to do with whatever has happened until this epoch. Let me call it T1. This is T2. Now look at this time, T1 to T2. So T2 is the time at which the next event occurs. Now this length of time, T1 and T2 minus T1, these are independent, identically distributed. Identically independent because we are sampling out from this initial probability vector the state to start for the next event. And so, because this choice of the initial state is independent of whatever has happened up to this time, these two turn out to be independent. And therefore, successive sojourn times, so T3 minus T2, all these random variables are independent. Now, suppose we move to the next stage, namely map. So we have a Markov chain labeled with the states labeled as 1 to M. Unlike in phase state distribution, we don't say a particular state is absorbing. I can call every state to be absorbing and every state to be transient at the same time, because the transition will be taking place. Then with a transition, an event occurs. So simultaneously, the state to which the transition has taken place will be the starting point of the next event. So we have a Markov chain on the state space. We have an initial probability vector as here, but this one will be in play only for initially. Thereafter, it has no role. But this transition probability matrix, yes, it has a role to play. This is a one-step transition probability matrix of the Markov chain. This is M by M. When I consider the phase state distribution, because there are m+1 states, so my matrix will be Pij, which is m+1 by m+1, unlike in this case. And therefore, there is an absorbing state, so that column vector of the corresponding this absorbing state will have elements depending on whether something will be, some transition to that state occurs, and what is the probability for that, that would be entered there. So now P equal to Pij, this is now M by M matrix. Only the first M elements of the phase type random variable would be available here, no absorbing state as such. So then what happens? Suppose, so we start here. So the initial state is picked up according to this initial probability vector alpha bar. So some state I just pick up. Now the transition among the all the states will be taking, some or all will be taking place. Successive sojourn times are exponentially distributed, so it is according to a semi-Markov process within that until the first event occurs. So this is time 0. Then we have the first event occurrence, which means that, so this event occurrence takes place. Suppose we are just at this epoch, and the next transition takes place after sojourn time here in the state, call it K. Now the sojourn time here is exponentially distributed with parameter depending on K and the state to be visited next. So I will call it UK, and suppose it is transiting to J, and with that transition, so it has come to this point, time is, so much time got elapsed. So RKJ is the parameter of the exponential sojourn time of this random variable, the amount of time it is going to stay here. And with this transition, an event also takes place. So first event takes place at this point with this transition. And the starting point of the next event is going to be the state J. It starts now in state J. Therefore, there is no more role for the initial probability vector. So what is the consequence of this? The consequence is that, for example, Tj, T2. So now we have T1, then T2 minus T1. These are successive inter-occurrence times or consecutive inter-occurrence times. Now these two get correlated, unlike in the phase type distribution, in the phase type renewal process. Because in phase type renewal process, we are sampling out. Every time an event occurs, the initial state for the next event is sampled out from alpha bar. Whereas here, that is not what is happening. It has already played its role initially and stopped. So this goes like this. So then these two are correlated. Then T2 minus T1 and T3 minus T2, these are correlated, T2 minus T1 and T3 minus T2, these are correlated. So it just, so that means two consecutive inter-occurrence times get correlated. So in addition to the semi-Markov transition process that is taking place, the successive consecutive inter-occurrence times turn out to be correlated. Now, if it is a service process, again, for example, according to a Markovian service scheme, same thing is repeating there. But then, in the case of service process, unless there is a customer, there will not be anybody to be served, and therefore, the states like this, where the next service is to start, will be freezed until the next customer arrives, and his service starts. And therefore, it's again a process like what is stated in this one. Only thing is that a freezing takes place in the absence of a customer in the system at the end of a service completion. Now, what happens from pH where there is a transitions within two successive sojourn times are correlated. They are exponentially distributed, they are correlated. But between two phase type events, there is no correlation. Two successive or consecutive phase type random variables. But coming to this one, two consecutive random variables also get correlated. Not only within this part, there is correlation among the random variables, means consecutive random variables. Here it is between also. So we have moved one stage higher from phase type to the map. Whether it is MMAP or BMAP, the same thing is happening. In MMAP, Markov in arrival process, well, we have different categories of customers arriving to the system. And therefore, it is referred to as Markov in arrival process. So if there are k distinct types of customers, then that will be represented by the matrix D0, no arrival, D1, customers of the first type, and so on, customers of the kth type. So they are all in singles. Arrivals are in singles. And therefore, MART would mean that this has probability P1 of first type of customer, arrival has probability P1. And arrival is of the first type with the probability P1, this is with the probability Pk. Here, no customer arrival takes place. So it is all rates of transition here without an arrival and the rest with arrivals, but specifying the type of customer that has arrived. In BMAP, what happens? It is a sequence of, so if you just have these two elements alone in this k plus 1 tuple, then that means these two alone, then it is the MMAP. Oh, sorry. It is it's the map. It's the map. In BMAP, what happens? BMAP, we have a sequence of matrices D0, D1, so on. D0 is transitions within the states of the Markov chain without an arrival. D1, exactly one arrival takes place, transition rates with an arrival. So K, D sub K would mean transitions with a batch of arrival of a batch of size K. This can be a finite sequence or an infinite sequence depending upon whether you impose an upper bound for the batch size in the batch Markov in arrival process. And since transitions are again according to the Semi-Markov process, so naturally it happens that successive inter-arrival times in this all are correlated. So starting from MAT, the successive inter-arrival times also get correlated. Now we go to something beyond. Yeah, these things are just explained in this slide. This also gives the description of now the Semi-Markov process. Evolution of pH distribution, well, I had just indicated it is within a pH distribution, it is semi-Markov, but not between two successive or consecutive pH distributions. In MMAP, all these things, consecutive interoccurrence times of events are correlated. However, in MAP, MAP or MSP, MAP/MSP2 with a single server or multi-server system. Arrival and service processes are not interdependent. So this is the concept that I propose to bring in, interdependence. What is interdependence? That I will be just introducing shortly. By considering the product space of the Markov chains generating these processes. So in a MAP, MSP single server or multi-server queue, we are going to speak about the interdependence. Just to introduce this for the time being, and then I will go to some other slides and then come back to this discussion again. So interdependent processes. Assume there are n processes evolving together. If the orders of the Markov chains generating them are taking place with the sojourn time in a state exponentially distributed. So now we specify the sojourn time in a state. State is n-dimensional state, not one-dimensional. So earlier, the semi-Markov processes that we discussed were all one-dimensional. But now we move to higher dimensions. And then the transitions will be taking place according to the semi-Markov process. I should mention at this point of time that the sojourn time in a state need not be essentially exponentially distributed, but things then will become more complicated. And therefore, let us now consider in our semi-Markov process the sojourn time in any state to be exponentially distributed, not arbitrarily distributed, not generally distributed. And of course, the parameter of the sojourn time will be depending on the state in which it is in and the state to be visited next, which is determined by a Markov chain, n-dimensional Markov chain. Not order of the Markov chain will be equal to actually the product that was indicated there. This one. The product M sub I. Now, I go to slide 14 because then I will come back to this one because this is a later, much later work. I start with Adan and Kulkarni. This was the first paper that came to my notice where some sort of interdependence was introduced. So they consider a correlation, correlation between inter-arrival time sequence AN. So inter-arrival time sequence would mean that time until the first arrival. T0 equal to 0. T1 that is taken as A1. Then T2 minus T1 is A2 and so on. So with that, we have this sequence of inter-arrival times, and then we have a sequence of service times of these customers. Sn, that's the second one, the second sequence. Now these are assumed to be correlated. That means there is interdependence of the service and arrival process. He has not assumed anything specific for the inter-arrival times. A generally distributed inter-arrival time is taken into, they have considered. Adan and Kulkarni considered the inter-arrival time distribution to be general. But whereas service time, they have fixed it as phase time. And then they compute the joint Laplace transform. So An and Sn are assumed to be interdependent. And then they compute the joint Laplace transform of this randomly, this pair. There are two other papers that came to my notice at that time. One is in 1979, which was discussing an MM1 simple classical queue with interdependence of arrival and service. And the second one, which appeared in 1999 in a conference in Japan, that is multi-server queue. Instead of one server, they considered 3 servers. Again, interdependence is assumed. So what happens is that later results subsumed all these results that were obtained by the people who wrote the papers on MM1 and MMC queues respectively with interdependence. So that paper, those two papers I am not going to speak about here. But then to me the real shock came when I noticed a paper of Buchholz and Krieg. There they spoke about interdependence and in a rather very general setup, but they were only looking at estimation of parameters. So the estimation of parameters, that part, they stated that it was not done by a paper that they referred, which was a paper by Benny Van Hoot, which was really a very general one. But then when I looked at Buchholz and Krieg paper, I also found another paper, which is by Bhaskar Sengupta. That appeared in 1990 in stochastic models, where the interdependence was really discussed, interdependence of arrival and service. So just to say one or two sentences about that work. So studied a first come, first served single server, semi-Markovian queue. There is no mention of the distribution. So you can have semi-Markov as an arbitrarily distributed sojourn time in states. That is also taken care of. Both the arrival and service mechanisms are semi-Markov processes. The inter-arrival time and service times may depend on one another. That means interdependence. They have already discussed. So this distribution of the service time is assumed to be phase type. That is, distribution of the marginal depend on one another, and the marginal distribution of the service times is assumed to be of phase type. Continuing that discussion on that, shown that the distributions of waiting time, time in system, and virtual waiting time are matrix exponential. Really very interesting results. These matrix exponential distributions have phase type representations. For the special case, when there is no interdependence, that is the important thing. So underlining that specific characteristic, when the inter-arrival times are independent of the service times, it's shown that the queue length distribution is matrix geometry. So the independence of the inter-arrival times and the service times, that means no interdependence, that gives rise to a matrix geometric solution for the distribution of the Q length. That was a really remarkable achievement. And for that special case, he proved that the Q length distribution problem is the dual of the waiting time distribution problem. That's a quite interesting result, which means that finding the solution of the first one, that means Q length distribution, also produces the solution to the other one, namely waiting time distribution. So that was though it was a shock to me, it was really a good news in the sense that somebody has already done a work. Bhaskar Sengupta is from India. Then, from that, Benny Van Hoot took the thread and he moved forward. So he published a paper in Performance Evaluation 2012. There, he started with the work of Bhaskar Sengupta, and then so this means the broad class of semi-Markovian queues introduced by Sengupta, he studied. This contains many classical queues such as GAM1 queues, SM, that means semi-Markovian arrival, MSP should have written as MSP, Markovian service process, single server queue, and several others, as well as queues with a correlated inter-arrival and service times. Now, queues belonging to this class are characterized by a set of matrices of size M. Now, in fact, Benny does something far beyond that will be just seen shortly. In fact, earlier, Sengupta showed that its waiting time distribution can be represented as a phase type distribution of order M. But then he has not made certain computation. That is, in fact, in the second bulleted item, if you just look at this shown to be phase type of order M, but no derivation for the Q length was provided in the general case by Sengupta, which gap Benny filled. So Benny introduced phase type representation, kappa, little k and capital K. So this you can regard the little k as the initial probability vector, and this is a capital K, uppercase K, of order M square for the Q length distribution in the general case, and proved that this order M square cannot be further reduced in general, which means that a sort of a minimal representation he has obtained in this specific case. So a matrix geometric representation, now just to see, there are matrix geometric representation, usually we have only two elements, but here there is an additional element. How it comes into play? That's the interesting thing. Suppose a customer completes the service when he completes the service, and that service completion is in some state, let us call it new or J in general. So an additional coordinate is just brought in here. That is this new. So this is established for the number of type tau. So a customer will be referred to as of type tau provided when he completes the service in a state belonging to that particular tau. In fact, that is the thing that is indicated by the last element in the triplet. So that is explained in this bulleted item. These results in both discrete and continuous time are derived. That is, in fact, a sweeping situation that he has looked into both the discrete case as well as the continuous time case. Further, he discussed the numerical procedure to compute this representation kappa capital K nu. When the arrivals have a Markovian structure, so earlier why I did not mention Markovian structure, because it need not be according to a, what you can call, the transitions need not be according to a semi-Markov process. No, it is according to semi-Markov process, but not according to exponentially distributed random variables. And therefore, you cannot expect a tridiagonal structure. But when the arrivals have a Markovian structure in addition to service process. So the arrival process, when that was in fact the earlier discussion, it was all concerned with semi-Markov transitions, but Sojourn times not necessarily distributed according to exponential random variable. So when these have this that particular characteristic also, that means Sojourn times in states are governed by exponential distribution depending on the state in which it is in and the state to be visited next, irrespective of whatever the dimension. The numerical procedure is reduced to solving a quasi-birth-to-death process for the discrete time case and a fluid queue for the continuous time case. So he has done extensive research in both continuous time and in discrete time. Finally, by combining a result of Sengupta and Osawa's paper appeared in Questa Queuing Systems in 2006. A simple formula to compute phase type representation of order M of the waiting time in a map MSP1Q without correlated service and interarrival times. That means no interdependence. Using the R matrix of quasi-birth-death Markov chain that is derived by him. So this is about Benny's work. Now I go back to the paper by Buchholz and Krieg. So that was this. It started on slide 14. So I'm moving to slide 14. Yeah. Oh no, it is not this one. Slide, I should call it. Oh, why it is not moving backward? Yeah, now it is moving. Yeah. So Buchholz, Peter Buchholz and J. Krieg, they were looking at the fitting part of correlated arrival and service times and related queuing performance. That is because for them, other parts were already taken care of by Benny. So they looked only at the specific parts of fitting the estimation side and then fitting the curve. So they considered a queue where interarrival times are correlated and additionally service times are also correlated with interarrival times and service also correlated. And service times need not be essentially correlated. For example, phase tape distribution. That is what they have considered. Therefore, service times are not correlated, but interarrival times and service times are correlated, are interdependent. And what they have considered is a map MMAP K PH K 1Q, meaning that there are K types of customer arrivals, so can be called priority 1 to priority K. Therefore, it is Mark-to-Markov arrival process. And therefore, the services also will be, service time distributions are also distinct for the K types of customers. Therefore, there are K types of services. One for one type of customer. For two distinct category customers, service time, random variable, phase type random variables are different, but it is served by a single server. Oh, that's all. Oh, I'm sorry, I'm just left with only 12 minutes. I'm going to do quickly. So the major result of this paper is the presentation of the approaches to fit the parameters of the model, namely the MMAP, the pH distribution, and the parameters, introducing correlation with the inter-arrival and service time, according to some trace of inter-arrival time and corresponding service times. So then the details are in the next 2 slides. Now, thereafter, it is Adan and Gurgan. I just, that is in fact much older. Now, I move to slide 24. Yes. So, Semi-Markov process in higher dimension. Essentially, what I talked about in the review of work done, they are all higher dimensional Semi-Markov processes. And how interdependence comes into play, I shall demonstrate in the slides to follow. So the Semi-Markov process that we discussed so far, initially in the phase state distribution, in a map, in BMAP, renewal processes, they were all one-dimensional. Assume their dimensions to be M1, M2, Mn. Suppose we have now n such distinct phase state renewal processes or map renewal process, correlated renewal process such as map or BMAP, whatever. So we have n distinct underlying Markov chains along with the corresponding initial probability vector and one-step transition probability matrix. Now, what we do is look at the product space. Now, when you look at the product space, a very important thing that you have to remember is transition taking place on these n-dimensional objects as in either a map, pH or map or BMAP, except that the dimension now is n instead of 1. The infinitesimal generator of this process is sparse. That's a very important observation. Transition rates between two distinct states is 0 whenever two or more corresponding coordinates in the two differ. Because, say, in a one-dimensional Markov chain, there was no problem. A transition from I to j. These are all scalars. But then, suppose I have IL to jk, that means two dimension. Then what happens? If, for example, the transition is from here to here with the j different from I and k different from L. So these two are distinct in the sense that first two coordinates do not agree, second two coordinates also do not agree. In that case, such a transition rate has corresponding rate equal to 0. In a short interval of time, such a transition cannot take place. Though, according to the Markov chain rule, of course, a transition from IL to JK is possible with positive probability. Therefore, in this transition probability matrix, one-step transition probability matrix of the corresponding two-dimensional Markov chain, we have to assume that these transition probabilities are 0. These are transition rates corresponding. So because we have taken this as 0, so there is no point in taking 0 here. But if you give a positive probability here, then there will be a real difficulty. So now the matrix has become sparse. That has helped us quite a bit. So yes, with that, though the dimension is increasing because of the sparsity of the matrix, we can do a lot of computations without much of problems. But then, however, Vishwanath, he is with the Government Engineering College at Thrissur. He developed an ingenious technique for reducing the dimension to study the system numerically. Thus, one can either proceed with the sparse matrix that I talked about, or go to Vishwanath's procedure. But that is again, I'll just indicate what it is. I naturally prefer Vishwanath's procedure because it has some interesting aspect. The trick is in defining the Kronecker sum. Usually we define the Kronecker sum of two matrices, two square matrices A and B as A Kronecker sum equal to A Kronecker B, Kronecker sum B equal to A Kronecker I, identity matrix of order B. So I'll write sub B, which means that having the order of B plus I identity matrix of the order of the matrix A, Kronecker product with B. Now this is changed by Vishwanath. This definition of Kronecker sum is changed. This is replaced by an arbitrary but just a diagonal matrix. Oh, sorry, I should not have written there. You will not be able to see that. No, that part was missing. So now what I do is the Kronecker sum of A and B, I'm going to redefine like this. A Kronecker B, Kronecker sum B equal to A Kronecker identity matrix, not identity matrix, instead it is a diagonal matrix of probabilities. So I will just say P1 so on. Dimension of B, suppose it is n, I write like this. Then plus diagonal matrix with a probabilities Q1 so on Qm, where Qm is the order of the matrix A and this Kronecker product B. So this redefinition, and then the advantage is why he did it, because from interdependence, well, you can analyze that, plus you can easily go to the independent case of the two processes. That means if you replace this diagonal matrix by the identity matrix, which is a particular case of this diagonal matrix, then it is a usual Kronecker sum. You get independence of the two processes. So that way, he successfully did the computational procedure. Now, quick application. There are numerous applications. I need not have to just say interdependence, the application part of the interdependence. Name any area of study, any branch of study. There, I can just point out some sort of interdependence. There should be two processes involved, that is all. At least two processes. I conclude with four examples, in fact. It is for the MAP MSP1 single server process. So this is a paper under review in Analysis of Operations Research, authored by Zenilal, Joshua, Dmitri, and myself. So the map arrival process has dimension M, D0 and D1 are the rates of transitions, D0 without an arrival, D1 with an arrival. And the service time dimension N, S0 and S1 will take care of that. The product space has M into N elements. But then it is two-dimensional, M by N matrices, so M into N elements. And if you look at the Markov chain, it is a two-dimensional Markov chain. The product space has Mn elements. Consider the Markov chain on this product space. We needn't have to worry about the initial distribution, obviously, because it is map and MSP. Now, how the process turns out to be interdependent is just indicated in this. So I will not go into further details, because now that is easily demonstrated here. Probability of, if you have two Markov chains, then this joint conditional distribution, probability distribution, equal to product of the independent part. You know, is all. Oh, 4 minutes. Okay, I will complete it in a 1 or 2 minutes. So combined Markov chain has a correlated structure because we assume that they are interdependent. So it is this sort of relation and not the one that is indicated here that is prevailing. So they are interdependent. Now, the examples. Weight Indian distribution of a tagged customer is shown to be phase tagged. Expected duration of the busy cycle is computed. The example, the fundamental arrival rate, because it is mapped, this is what is indicated. Correlation turns out to be this. So, 4 examples where correlation in one is positive, whereas the other is negative. And then both may be positive, both may be negative. All these 4 things are considered. And the consequence is, in the case of interdependent arrival and service process, the expected number of customers in the system is this much. That means 1.8821. Whereas that in the independent case, that means when the arrival and service are not interdependent, then the number of customers is getting considerably reduced. That means with the introduction of the interdependence and with the arrival process having a negative correlation, service process having a positive correlation, the number of customers in the system is larger for the interdependent than in the. In fact, this is what we have seen throughout, irrespective of whether they are positive correlated, arrival process is positive correlated, service process is positive correlated, or the other way, or both in different way. So we have all these results. And example 4, again, well, both are essentially having negative correlation. So we have got these results. Probability of number of customers in the server busy. In fact, the last one, PB, stands for probability of number of probability that the server is busy. In interdependent case, naturally, we should expect the server to be busier for a longer time than that in the independent case. So thank you for the attention. Any questions? I will try to answer. Hello? I have concluded.
Thank you very much, Professor Chakravarthy. Thanks.
So no
Question,
question,
please.
pardon me? Hello?
No question.
No question. Oh, no questions. Okay, thank you very much.
No question.
No questions. Okay. So thank you very
much.
Thank you very much for the patient attention. Thanks all. Thank you.
Thank you.
Okay.
Now we have 30 minutes coffee break. 30 minutes. Thanks. Okay. We continue our plenary reports, and I would like to give the floor to Professor Nikitin from Seattle, United States of America.
Здравствуйте. Can you let me have the control of presentation, please, so that I can share the slides? Если вы меня не слышите, я попробую еще раз сказать. Мне нужно, чтобы я смог свои слайды начал показывать. Мне нужно нужен контроль над презентацией, потому что я не вижу себя этого.
Я вам дал вроде сейчас.
Сейчас.
Вы меня включили?
Сейчас попробую.
Pavel, just a minute.
Just a minute. I apologize for the delay to all the participants. I'm trying to figure out how to share the slides.
Да, мы слышим вас.
Скажите, пожалуйста, если увидите первый слайд.
Первый слайд. Мы видим и слышим вас.
Видите слайд и слышите меня, да?
Да, да.
Да. Хорошо. Спасибо. Sorry for small delays figuring out the presentation. My name is Pavel Nikitin. I live in Seattle. I work at Impinj, and I also work at the University of Washington. I am very honored to be presenting here today. I was at your conference 3 years ago, and I hope that the next time when your conference will take place normally, not virtually, will be sooner than another 3 years. Thank you for organizing it, and once again, it's a big pleasure for me to present here today. The topic of my talk is RAIN RFID technology, past, present, and future. Just a quick check. Can you see the next? Oops. Can you see the next slide? Just to make sure that it transitions.
Yes, we can see.
Okay, great. Thank you. So there will be 3 parts to my talk. I'll talk about the past of RFID because it's really a fascinating technology with a very rich past. I will talk about the present state of the technology, and including products, applications, hardware, and we'll try to see what interesting research problems are out there and what lies in the future. So what is RFID? RFID is one of many OTID technologies, but it's a wireless OTID technology. And not only it's a wireless OTID technology, it's a passive OTID technology. It's based on modulated backscatter, where tag itself is not a source of RF energy. This is the big difference from conventional radios. So RFID allows you to identify and authenticate an item. And you might be surprised to hear, but there are already billions and billions of RFID tags out there in the world. They are not all connected to internet. A lot of them are connected to private networks. And a very good example is many marathon races use UHF RFID for tagging participants. Usually the tags are attached either to the running shoes or to the bib. The picture that you see on the right is the picture from New York City Marathon, the aerial view. The number of participants there is about 50,000. So every participant has an RFID tag. And of course, it's all managed privately as a private network. So they just get the timing, that's it. But the number of tags grows. And in last year alone, there was about 20 billion tags that were sold. Most of them were UHF tags. Now, what is the difference between UHF and other RFID systems and tags? So RFID is a very generic term, and it can be low frequency, high frequency, or ultra high frequency. So today I will talk specifically about the area where I'm working, which is UHF RFID, also known as RAIN RFID. LF, low frequency and high frequency RFID are inductive coupling systems. UHF RFID is a long range technology. Basically, it's a far field technology. And if you have never heard about RFID, a very simple analogy to explain how reader reads the tag, if the tag doesn't have any power source of its own, it can be a flashlight analogy. Imagine that there are two people communicating. One has a flashlight, another person has a mirror. So when you want to send bits, the person with a mirror can just flip the mirror with a non-reflective side. The process of flipping the mirror takes very little energy, and the person with a flashlight can detect the presence of reflection and know if it's a 0 or 1 coming. Another good analogy is when a radar tries to detect an airplane and sees two airplanes, one with a large radar cross-section, another one with a small radar cross-section. So as I mentioned, LF and HF RFID use lower frequencies. So LF is in the hundreds of kilohertz, HF is in the tens of megahertz. Because those are inductive coupling systems, the range is typically limited to about 1 meter. But also they do penetrate materials much better. That's why, for example, the tickets that are used in subways all over the world are typically HF tickets. However, the advantage of UHF RFID is not only the read range, which can be up to 25 meters with modern ICs, it's also much higher data rates. So the current standard allows up to 640 kilobits per second. I think I have this field blank, I forgot to fill it, which translates to about 1 to 2,000 tags that can be read per second. It's interesting that RFID technology has its roots, which trace back almost 100 years ago. The very first patent that was filed on a modulated backscatter system was filed in 1924 in France. The patent was for the radio telegraph or radio telephonic communication, and the patent was basically for having a key that was connected to a separate loop, and it had a capacitor. So shorting and opening that loop would create a different load on the main coil, and this way you could basically send the signal without having your telegraph key physically, electrically connected to the main apparatus. In 1930s, modulated backscatter received a lot of attention because the role of aviation in the war was proved by World War I, and it was clear that World War II was imminent. So British started very intensive research that would help them to identify, to tell the difference between the enemy airplanes and their own airplanes. And one of the early prototype systems that they came up with was called IFF. There was an antenna that was stretched across the wings of an airplane, and there was a mechanical switch in the middle of that antenna. So the antenna was opened and shorted 10 to 20 times per second. So a radar could theoretically detect the backscatter signature, and if the motor was running and that switch was turning on and off, the radar could look at the frequency of shorting and basically make a decision if it's a friend airplane or enemy airplane. Unfortunately, radar range at 1930s was very short, less than a kilometer, and if an enemy airplane gets to you to within a kilometer, that's typically too late. But this, nevertheless, is basically an example of a fully functional modulated backscatter RF system that was built in early 1930s. At the bottom of each slide, I give a link to the source. Typically, it's a book or an article, so that's where you can find more information. Let's take a look at 1940s. There was an interesting thing that took place right after the World War II. Soviet pioneers gave as a gift to the US Embassy in Moscow a wooden carved seal, basically an American eagle carved in wood. It was fairly large, very delicate, very beautiful, so an ambassador hung it in its boardroom. And very soon, Americans noticed that sometimes very important information became available to Soviets. They were looking for a device for several years, for 6 to 7 years, and finally, with the help of MI6, which is British service, they found it. When they found it, they still couldn't figure out how it works, so it took some time, because remember, at that time, 1940s, so all the radios were typically heavy, with batteries, with vacuum tubes, etc., etc. This was a light device without any power source of its own. It turns out it basically was an RFID tag that was loaded with a very sensitive microphone. So whenever somebody in the room was speaking, and if a special car was parked in front of the embassy with a special high power RF source, basically that car could detect the reflection from that embedded tag. I don't even know what kind of power was transmitted by that car, because that was, of course, before all the regulations took place. That device, the replica of this device, is on display in National Cryptologic Museum close to Washington, D.C. I visited it a few years ago, and it's really worth a visit. So when the borders open and you guys start traveling, I highly recommend you that if you're in DC area to go to that museum. It's open to the public. The person behind this device was Leon Theremin. He was Russian. He was born in St. Petersburg. He served in World War I. And he, after revolution, started working at IOFA Institute. He had a number of different inventions. For example, he was dubbed as a Soviet Edison because he met with Lenin multiple times, and Vladimir Lenin was extremely impressed by him. He also worked on alternative television system and was quite successful, but of course Zworykin was more successful. In 1927, Leon Theremin came to the United States, and he continued to work on different things, which included alarm systems and different contactless musical instruments, because one of his creations was called Therminvox, or Etherophone. It's basically an amplifier with, let's say, 2 antennas, where the proximity of hand to one antenna controls the frequency, the pitch, and the proximity of a hand to another antenna controls the volume. He was extremely successful. He gave a number of concerts. He got patents. Therminvox was licensed by RCA, an American company. Abruptly, all of a sudden, he returned to Russia. There are still theories why that happened, and he was imprisoned for 8 years. So during that time, he started in Magadan, but then he was transferred to Moscow. He, according to his memoirs, he worked alongside with Sergei Korolev at that prison, who was, as all of you know, the father of Russian cosmonautics. After the release, he was given a Stalin Medal, but a number of things happened, and his life is, there are books that have been written about his life. He ended up working as a technician at Moscow State University at physics department almost until his death. He died in early 90s. He was 97 years old. And Albert Glinsky wrote a great book, which is called Theremin, Ether Music and Espionage, which I highly recommend you. So Leon Theremin can be considered a creator of a first fully functional passive RFID tag. On another side of the ocean, there is another person who made a significant contribution to the modulated backscatter technology. And his name was Harry Stockman. So Harry was born in Sweden and he got his PhD in Harvard. He worked for many years at Cambridge as head of the communications department, working on military projects. And one of the projects that they worked on was they were trying to figure out if it's possible to convey an information from an airplane to the ground by mechanically moving some parts of the airplane. So he made a few mock-ups, and some of his mock-ups included those mechanical concoctions, which were on the same axis, and by rotating them with different speeds. So what you see here on this photo is basically a mechanical 3-bit tag. By rotating each of the 3 parts with different speeds, he was able to convey like a 3-bit number back to the transmitter. He wrote many interesting articles in all areas of electrical engineering. And interestingly enough, one of his articles is called Use of Educational Aids in Electronics. The picture that you see here, where there's a person lying on the bed and watching a circuit diagram being displayed on the ceiling, is Harry Stockman's idea of how undergraduate students in Harvard should be studying circuits. Well, a lot of us, as you know, are working and studying from home nowadays. So I think that picture has a lot of relevance to the current situation. Let's move on to 1950s. In 1950s, people start getting really interested in RFID technology, and there are 2 key patents that were issued at that time. Both of them were based on functional hardware systems. One of the systems I found especially interesting. It was a 3 gigahertz system with a 25-watt transmitter. It had 100-meter range, and basically it allowed the transmitter to hear the voice that was spoken to the passive modulated telephone. But in order to achieve that range, they used 40 dBi parabolic antenna. So you can imagine the size of this antenna, and you can also imagine the amount of power that was radiated, 25 watts plus 40 dBi. In 1960s, people start getting interested in the US about commercial applications of RFID. So there are 2 companies, Sensormatic and Checkpoint Systems, that realize that there is a big potential in what is called the EES, which are loss prevention systems. Basically tags that go on different clothes and garments so that when people try to steal something from the store, it triggers an alarm. And at the same time, IEEE community got interested in this problem. What happens when you take an antenna, when you load it with different impedance loads, what happens when it reflects the signal? There were some very nice key publications in IEEE transactions on antennas and propagation that happened around that time. In 1970s, the government comes in, and they start also looking at this technology. So one of the labs that was involved was Los Alamos National Lab. They looked at RFID for tracking assets in military, but they were also open about publishing. And out of that lab, there came a very interesting publication. It was a cattle tagging system. So basically a tag that goes onto the ear of a cow. And not only it goes onto the ear of a cow, it also measures the temperature of a cow. And the tag was fully passive. And the tag had a 3-digit ID, and it could basically sense the temperature. And the range was very decent, 5 meters. And it was operating in the band 915 megahertz, basically 1 gigahertz, that UHF RFID is using today. So that was basically a first fully functional prototype of a complete RFID system. And also worth mentioning the very first patent that fully describes RFID system with memory, not just the physics of the modulated, backscatter. was Mario Cardullo. So Mario Cardullo, I met him at a conference a few years ago, and he's still very active. He still patents, he works on RFID, and he's just a very interesting and very smart gentleman. So in 1980s, two applications receive a lot of attention. One is electronic toll collection. People realize that using RFID tags is a great way to basically figure out if the car passed a certain bridge or not. Several countries start implementing it. In US, it mostly happens around New York area, but in Europe, Sweden was very active in those efforts. In 1980s, if you look at the tags, and here are the pictures of a couple of tags, let's take a look at the tag on the left. What you notice is that there is a integrated circuit, which is this, in the bottom right corner. That's basically where all the digital electronics was implemented, that was handling the protocol, etc., etc. But all the RF components were still implemented with discrete elements. That's why tags were, fairly expensive and, fairly large. Also interesting that in 1989, for the first time, the term radio frequency identification becomes staked in IEEE, because before people were calling it modulated backscatter, reflected backscatter, different things. From now on, they call it RFID. In 1990s, people tried to figure out what should be the standard for UHF RFID, because RFID finds deployment in more and more different ways. Railways use it for tracking cars. As I mentioned, it was used for car tolling. A lot of it was used for access control. Several big companies, IBM, Fairchild, Motorola, start working on RFID, on UHF RFID. When I say RFID, I mean the long range UHF RFID. And at that time, so there are as you know, there are several ISM bands, unlicensed bands, like 915 megahertz, 2.4 gigahertz, and 5.8 gigahertz. At that time, still both bands were considered, 915 megahertz and 2.4 gigahertz. But eventually people settled on 915 megahertz band because of the range advantage. Because at the lower frequencies, the path loss is lower, and basically you can collect more power. And at that time, the sensitivity of the ICs was fairly poor, maybe minus 7 dBm, minus 8 dBm. So the decision was made in favor of 915 megahertz. But of course, the trade-off was that at 915 megahertz, the wavelength is about 30 centimeters. So all things are bigger. So nowadays, when people are trying to think about miniaturizing RFID readers and building them into smartphones and miniaturizing RFID tags so that they can fit onto small items, unfortunately, 915 megahertz doesn't really play to our favor, because of the physics, the wavelength is too large. A significant development that happened in 1990s, CMOS Schottky diodes were created and commercialized. And all of a sudden, it became possible to implement the whole RFID tag, including the analog part and the digital part. So at the analog part is basically RF to DC conversion, the modulator, and the digital part, all in one single integrated circuit. So the tags from now on look like something that only has two components. One component is antenna, and another component is a chip. So there is a great article which was written by Jeremy Land, who was and is still one of the key people in RFID. It's called The History of RFID. It's available on IEEE, and I highly recommend it. It basically covers briefly a lot of the things that I talked about, but from slightly different perspective. In 2000s, quite a few companies entered the RFID market, and they start specializing. Some companies make only readers, some companies make only ICs, some companies only make tag antennas, and some companies make software, and some companies try to do everything. All of a sudden, there was a big demand for RFID that was driven by Walmart's statement that Walmart will use RFID tags, UHF RFID tags, on every single item that it sells. That really boosted the industry, and people started investing into RFID. And in Europe, an equivalent initiative was done by Metro AG. So Metro AG is a very large network of stores. I think they are mostly known in Germany, but they're all over Europe. So they also announced that they want to convert these stores to be fully automatic so that every single item is RFID tagged. That effort went on for several years, and eventually both Walmart and Metro AG abandoned the efforts just because they couldn't get the required accuracy. The problem with RFID is you don't need to see the tag to read it, but another side of it, you're reading something and you don't know if that's the tag that you need to read or not. Maybe it's the tag behind you that you really don't want to read, but because it's RF, you just happen to read it. The Gen 2 standard was created and ratified in 2004. And another interesting and significant thing, there was a need for single lab that would certify which tags are good for certain applications, so that when companies, large companies like JCPenney or Macy, would like to deploy RFID in some of the stores, they would know that if they buy a certain tag, that tag would work, for example, well on jeans, but wouldn't work well on leather. So there was a lab that was created at Auburn University. It's called ARC. Right now, it's basically one of the leading certifying bodies for the tags. And what you see on the right is the anechoic chamber that they use, the items that they test tags on, and also several tag antennas. So tag antennas look very, very different. They're mostly like very simple antenna structures, but they're very carefully optimized in order to give the desired performance on a specific material, at a specific frequency, at a specific power, etc., etc. So it turns out that tag design is also a very interesting area of RFID, and we'll talk about it a little bit later. So today, RFID, UHF RFID, is governed by RAIN. It was decided to give to RFID its own unique name because UHF, is sort of a generic, old-fashioned RF term. So RAIN RFID plays the same role as NFC Forum or Wi-Fi Alliance or Bluetooth ZIG. And they have a website, they have regular meetings, and they have all the standards and documents posted up there. I would like to mention a couple of interesting facts. So the RFID chips nowadays are very small. They're on the order of maybe 0.5 millimeter by 0.5 millimeter. So it's a quarter square millimeter area. The number of transistors there is more than 500,000 typically, overall transistors. So it's larger than the number of transistors in Intel 286 processor, which was the heart of the IBM PC-AT. And I'm sure that there are some of you in the audience who still remember that machine. My university, Novosibirsk State University, where I went to, had quite a few of those at my time. Another interesting fact is the RFID IC consumes lower power than a honeybee's brain. So there were some interesting studies which concluded that honeybee's brain is super efficient and it's very complex. It actually can do a lot of operations while consuming very low power. So it's sort of a highly optimized low power microprocessor. And so RFID IC consumes an energy which is comparable or less than that, which is about 10 microwatts. A couple of the details about the how the Gen 2 UHF RFID works. So reader talks to the tag using amplitude modulation. It basically turns the power on or off, and the encoding that is used is interesting. It's a pi encoding. Basically, 0 is encoded as a waveform that you see on the slide, which is binary 0, and binary 1, the waveform the same, but the preamble is longer. And the reason why it's done is to maximize the power that's delivered to the tag, because it's a passive technology, so it's always advantageous if tag can collect as much power as possible, no matter whether it's 0 or 1 coming. And when the tag talks back to the reader, it uses FM0 and Miller encoding. I'm showing the waveforms here. It's always interesting to see how the new technology that is being introduced affects the number of patents and publications. So if you go to IEEE, and also if you go to any of the patent search engines and just search for patents and publications with the word, let's say, RFID in title, of course, there are many papers which use, or still use words like modulated backscatter and radio frequency identification. But if you just concentrate on, the keyword RFID, as of September 1st, there is about close to 11,500 of IEEE publications and about 6,000 US patent applications and about 4,500 of issued US patents. And if you look at the trends of IEEE publications with the number of years, you see that starting from early 2000s, it grows very rapidly from like 5-10 publications per year to over 1,000 publications per year. And then it subsides and sort of remains stable at about 600. It's actually quite typical for a lot of new technologies. So if you look at several other technologies and do the same simple research on IEEE or on a patent search engine, you will see a similar trend. So that basically shows that RFID is mature now, and it just has to be adopted. It just has to find the right application niche. A couple of words about readers and tags. So readers are direct conversion transceivers. They transmit and receive at the same time, which is basically just like a vector network analyzer. And they, just like a vector network analyzer, they can be monostatic or bistatic in configuration. The tag, as I mentioned, because all of the electronics is implemented in a single chip, when you look at the tag, it's just an antenna plus the chip. But inside the chip, you have the rectifier, you have the demodulator, you have a backscatter modulator, and of course you have a digital part. Basically, it's a low power state machine. So a couple of words about a link budget. So link budget, as all of you know very well, is very important when you design any RF system. You need to make sure that you receive enough signal in order to be able to hear the person whom you are trying to talk to. So the link budget for the RFID can be represented as sort of this chopped, I call it a chopped tree diagram. On the horizontal distance, a scale is the distance on the log scale, and on the vertical scale is the power also on a log scale. The reader transmits a certain power, which goes along the cable, attenuating very little. It comes to the antenna. Antenna has a certain transmit gain, so we see this little boost. Then it goes through the free space. Let's say it's for free space. So it reaches the tag. The tag backscatters. When it backscatters, it incurs a certain backscatter loss. The signal has to travel back through exactly the same channel because the system in this particular example is monostatic. It goes again through the receiving antenna and reaches the receiver. So the received power for the modern ICs, if you move the tag to the maximum possible range when it's still energized, can be as low as -94 dBm. And the reader can transmit up to 36 dBm. So we are talking about a system which must have 130 dB dynamic range. It's basically a system that can be compared in terms of RF performance to the best and the most expensive vector network analyzers. So RFID readers, especially the high-performing ones, is a very interesting area of research for hardware. So RFID tag, a couple of words about RFID tag. So the tag, I think I'm saying that already third time, so I apologize. It's just an antenna and an integrated circuit. So tag sensitivity is a function of both IC impedance and IC sensitivity. The backscatter signal strength that the tag produces is a function of IC impedance in both states. Because remember, when tag modulates, it switches the load between the two impedances. And so depending on the particular values, you can have strong backscatter or weak backscatter coupled with a strongly absorbed power or not so strongly absorbed power. It's interesting to see how RFID tag sensitivity changed over the years. So I don't have data for all the companies, but I have data for the company that I'm currently working at. So the very first chip that Impinj produced was in 2000. It was called Monza 1A, and it had sensitivity of -9 dBm. So that meant that basically it had a read range of about 5 to 6 meters. So over the years, the sensitivity improved. The latest chip that was released this year has a sensitivity -21.5 dBm, which means that it can be read at close to 25 meters with the right tag antenna. So the RFID hardware, if you're talking about RFID system, basically consists of three parts. two parts. I'm sorry, connectivity, which is readers, and the readers can be fixed, handheld, or embedded, and tags. And tags basically consist of antennas and ICs. RFID currently has a lot of applications, so ranging from retail stores, where some of the stores in Europe, for example, Marks and Spencer, put UHF RFID tag on every single label, on every single garment. Same goes for a lot of the Decathlon stores in France and in Italy. Supply chain and logistics, basically tracking all these packages that come into and out of the warehouse, and vehicle identification and tolling. The picture that you see on the left is the picture of the bridge in Seattle that goes across Lake Washington from Seattle to Redmond, where Microsoft is. And there are readers installed on that bridge. So every time when you cross that bridge, if you have RFID tag, you automatically get a certain amount of money deducted. And you are encouraged to have an RFID tag, because if you don't, you will still have to pay, because there are photos that take, there are cameras that take a photo of the license plate, but you'll have to pay more. So this way, sort of the RFID technology use is encouraged. There are a lot of applications for using RFID for attraction tickets by Disney, for example. Disney just launched, before the pandemic, Disney was going to launch, let me correct myself, a big program that would introduce RFID tickets in almost all of the amusement parks. Ski lift tickets, the tags are embedded in passports, in passport cards, used for baggage tracking, and another very large application that's very popular now is healthcare, basically tracking items inside the hospital. That becomes very, very popular. So that was sort of the historical and commercial and a little bit of a fundamental side of RFID. I'd like to talk a little bit about research, because a lot of us in this conference are academics, so we're always interested in things that can be researched and discovered. So there are several areas that present a lot of interest from the research point of view, and I will cover all of them in a little bit more details. But the first area is localization, and I would like to mention that, so IEEE is a great source for a lot of information, and for example, IEEE Microwave Magazine published this great article about 10 years ago, which is called "Where is the Tag?" Even though the article is almost 10 years old, it's still very actual, still very current, and it basically gives you a great overview of different localization algorithms. So how can you localize the tag? So if you've read the tag, how can you tell how far the tag is, where it is, in which direction, and maybe even where it's moving? So one way to do that is basically to have a beamforming antenna. So it's basically like a classical radar approach. You know, when you have a beam, you know, scanning across the sky, and you know, at some sector of the sky you find an airplane. But the links below point you to different IEEE papers on those topics. So an example of a beamforming antenna from one of the papers is shown on the left. It has 4 antennas, and it allows you to scan the beam in just one direction. So if you want to get a 2D beam scanning, you need to have a 2-dimensional antenna array, which becomes more complicated to design and of course more costly. Another way that you can tell where the tag is, you can have multiple antennas as shown on the second picture, and you can collect the tag signal, signal strength, RSSI, and phase, and record it on different antennas which are located at different locations, and basically pull together this data and try to figure out, for example, the angle of arrival. But another interesting approach is called synthetic aperture approach, synthetic aperture radar. So synthetic aperture radar, instead of having multiple fixed antennas that receive a signal from a source and thus compute their direction of arrival, you can have a single antenna that is moving, that receives a signal several times at different locations, and then combines the received measurements in order to reconstruct the picture that a large fixed array would receive. So synthetic aperture radar is actually used a lot in military because it allows you to basically map the area using a single airplane, map, you know, from RF point of view. And there are 3 interesting papers that I would like to mention. One, you see a person holding a handheld, And the idea is if you want to get a direction to the tag, and you can read the tag, but you cannot afford to have two antennas. You want to have nice small handheld. What you can do is you can move this handheld around. This handheld has a built-in accelerometer, so it can track where it is. And then you combine the received tag signal at different positions to basically get you the angle of arrival, direction to the tag. And there is a group at the University of Pisa, which is led by Professor Paolo Nepa, which also work on the synthetic aperture radar approach, and which has several interesting publications. One is the tags moving on conveyor belt on a predefined path. You can do a correlation and find out where the tag is by measuring phase and running the autocorrelation. And another one is what I mentioned, SAR being used in military. That group have successfully done a very interesting experiment where they basically flew a drone with a GPS and a reader on the field of above several different RFID tags, and we were able to successfully reconstruct the locations of the tags. Another example of a beamforming system is that I mentioned that allows you to track the angle to the tag in 2 dimensions is a 2-dimensional array. And again, the company where I work, they do produce such beam steering antenna system. It's called X-array. It's an array of several antennas, and it allows you to resolve tag location to about 5 feet in 2 directions, X and Y, and it can cover about 100 square meters. So there's more information at that link if you're interested. Another interesting research area, what you can do with tags is sensing, because modulated backscatter is very attractive candidate for sensing compared to active wireless technologies. We want our sensors to be low cost and low power because we want to deploy them everywhere. So if you think about it, the RFID ICs consume microamps versus milliamps that typical low power radios consume, and they don't have any battery. Or if they even have a battery, you don't need to maintain it very frequently. It can last maybe 10 years. There are several RFID sensing methods that I listed here. I'm a little bit running short on time, so I will just skip it for the brevity. But if you're interested in these different methods that you can do sensing with RFID, you can look at the links below. Another interesting area that I would like to mention is smart tags. So there are a lot of things that you can do with an RFID tag if you have an external microcontroller, external power source, external sensors, and external actuators. You can basically have a device which senses multiple quantities and actuates multiple quantities and behaves a certain way. It can have some cryptography. And 2 examples are this Ramses platform is based on Impinj Monza X chip. And what it does is it harvests power at 1 frequency band and it processes it. It has a bunch of sensors, but it backscatters at a different frequency band. So it's a dual band tag, basically. It's a fully passive tag, but it uses 2 different frequencies, one to harvest and one to backscatter. And another interesting application of a smart tag is the one that you see on the screen in the bottom right corner. As you know, RFID right now only uses amplitude modulation when the tag talks back to the reader. So it's basically just 2 impedance states. Well, there is no reason why there should be only 2 impedance states. There can be more. And as an example, this group at the University of Washington created an RFID tag with a QOM constellation of basically 16 points. They successfully built it, measured it, and it's like a miniature wireless system, except for it's fully passive. If you're interested more, there are 2 great open platform research projects at University of Michigan and University of Washington, and you can see the links below. One gives you all of the information how to build a passive UHF RFID system based on MSP430 microcontroller for the UHF band. And another one is the same, but for the NFC band, 13.5 megahertz. So they have schematics, they have board files, they have everything, and they're happy to collaborate with anyone. So from academic point of view, it's a great research resource. Another very interesting area is medical applications. If you think about it, passive RFID tags are ideal body sensors because they don't require any battery. So if we wear something, we don't want to change battery on the thing we wear, right? So, for example, I have a watch. It's an Amazfit watch. It lasts about 30 days on a single battery charge, so it's fairly low power. But I'd like it to last forever, and basically passive RFID tags do allow that to happen. There is a number of very interesting publications where people propose to put RFID tags on different parts of the body and detect the signal from the tags, and from those signals, RSSI, signal strength and phase, deduce what exactly a person is doing. Is he moving the right hand? Is he moving the left hand? So I include some screenshots and some links below. Another interesting area is unconventional propagation. So we typically, when we design RF systems, we always think either free space or multipass, free space or multipass. And there was a great talk at the beginning of this conference by Dmitri Moltchanov, which basically showed that the urban propagation environment is actually very complex. There is free space, there is multipass, but there are some other conditions. You know, sometimes buildings can almost act as channels, as waveguide channels. So in waveguides, the range of any system is longer because, you know, the waves do not travel in all directions, only in one direction. And there are a lot of practical waveguide examples in everyday life, starting from tunnels and mine shafts and aircraft body, and ending with shipping containers and gas and drill pipes. And so there are two works that I would like to mention. One is from Carnegie Mellon University, where it was proposed to use RFID inside heating and ventilation ducts, because heating and ventilation ducts are basically metal waveguides that run through the whole building. So it turns out that with a single RFID reader, you can cover multiple story building and read tags on multiple floors in multiple rooms. And there was another interesting paper by the same group from University of Pisa, led by Paolo Nepa, about using RFID tags inside metal pipes. So on construction site, they can be pipes, and it's really needed to basically accurately control which pipe goes where, etc. So the tag can be mounted either outside or sometimes inside. And if it's mounted inside, it's a classical problem of basically figuring out the EM wave propagation inside the waveguide. So that's another example. Another interesting area is tag-to-tag communication. There were several works. We started this research at the University of Washington about 10 years ago. I no longer do that, but I know that there are several other groups that continued it. And basically the idea is that if you have an external RF field, then two tags where each of the tags is fully passive, it doesn't have a power source on its own, when they are both placed inside an RF field, they can communicate with each other. It's like an equivalent of two people in a dark room. When there is no light, you cannot see another person. But if you turn on the light and you see another person, then you can start communicating by blinking, basically by modulating the reflected light. And there are several very, very interesting works in that area that I also recommend you to look at. And the continuation of that concept was done by University of Washington again. It's called ABC, ambient backscatter communication. And the idea is that there are actually a lot of signals on the air. There are Wi-Fi signals, there are FM radio signals, there are TV station signals. And sometimes those signals can be enough to energize a device and have this device backscatter. And in some cases, they can even make a backscattering tag mimic the backscatter so that the backscatter looks like a Wi-Fi transmission or a Bluetooth transmission, which means that you can have a fully passive RFID tag, which looks like a normal Wi-Fi source or Bluetooth source. Again, very interesting research, and I think there are still some difficulties in terms of getting the desired range, but I think we will see something coming out of that in the future. So, what will happen in the future? I would like to take a small lyrical sidestep to refer to the iconic movie, which probably all of us know, which is Back to the Future trilogy. So in 1989, the second part of the trilogy came out. And if you remember, Marty there travels by the flying skateboard. And so at that time, it was a complete science fiction. Only 25 years later, a Canadian basically built a hoverboard, which was powered by electric motors driven by the batteries, and he successfully traveled 275 meters on it across the lake. There is a company website, they design the boards, and they even have a US patent. Even though it's not a utility patent, it's a design patent, but nevertheless it's a patent. So dreams, even the wild dreams, can become reality. So what can be there, what lies there in the future for RFID? We believe, we at the company, the place where I work at the university, that Internet of Things will evolve just like Internet did, and RFID will be a major part of the Internet of Things. In the early Internet, there was a lot of private networks era before they all became combined together into one single global Internet. Likewise, right now, there are a lot of private networks of things. And one example that I gave you, maybe there is a Boston Marathon and there is a New York Marathon. And each of these marathons uses an RFID system, but each of this network is only local, is basically only limited to participants of that particular event, 30 or 40,000 people. But eventually, they will merge. And so we believe that it will be an internet of both devices and items, where a lot of our everyday devices will be able to read our items, and the information about those items will be continuously updated in the cloud. You say, well, what's a big deal? If I can read an item with an RFID tag and I know where it is, it might be sufficient. Well, when you read an item, you identify it, and maybe you can locate it, as I mentioned, using, for example, beamforming antennas. But if that item has a digital record on the cloud, and if you update that record, if you think about it, that record has now a full history about the ownership of this device, of this item, I'm sorry, whether it's a suitcase or a bicycle or a computer, who owns it, who bought it, what was done, the history of it, the services that were performed. If you sell it, you can transfer the ownership to another person. So you have a lot of opportunities there. And RFID is actually quite good technology for doing that because it has no batteries, it has sufficient range, and it's just right. So to conclude, I would like to say that in my opinion, and I hope that you agree with me at least partially, RFID is really fascinating wireless technology because it took almost 100 years to go from a concept to wide implementations that we see today. Compared to low frequency and high frequency RFID, it has longest range. Compared to any other wireless technology, including Zigbee, Bluetooth, low power, Bluetooth, and LoRa, it has lowest power and lowest cost of the radio. You cannot beat the cost of one single RFID IC, which is basically 1 cent. The system performance, of course, strongly depends on all the components, including the propagation environment. The wide adoption of RFID is happening right now, and as I mentioned, there are many interesting challenges for the researchers. I believe that as those challenges are being solved, there will be some applications that we do not suspect of today, but they will just emerge, they will come out. And I would like to refer to the cartoon by one of my favorite cartoonist. It's an American cartoonist who used to be a science teacher, Gary Larson. So in 1995, he drew this cartoon where a person comes out of the men's restroom in a restaurant, and all of a sudden the alarm bangs, which says, didn't wash hands, didn't wash hands. So that could be a perfect use of RFID technology. And once again, I think that it has a lot of relevance to today's situation, now that we have to wear masks and make sure that we wash hands and sanitize them very often. Just as a couple of last things, I know that I'm almost out of time. There is a number of RFID events. Some of them went virtual, like RFID conference and Rain RFID. Some of them are still planned in person. Of course, we don't know what the situation will be next year, but I highly recommend you that you at least look at IEEE RFID conference. and see what's there. It's the world's premier place to learn about what's happening in the world of RFID. About Impinj. So Impinj is located in Seattle. The little yellow circle shows our building. We are close to downtown. So our building is 11-story building, and Impinj is sitting on the last 3 floors. And we are actually making ICs for the tags. We're making readers, and we're also making software that manages the readers. I would like to thank you very much for your attention. If you have any questions, I would be happy to answer them. Or if you think about something, you can send it by email. And the picture that you see here on the right is Seattle in the morning, because right now it's 7:30 in the morning, almost 7:30. Unfortunately, there was a lot of forest fires in the last few days, and I think Arkady from Australia mentioned bushfires, which are a big problem, and forest fires are a big problem here. So today it doesn't look like that, but there are some days when Seattle looks like that. So once again, thank you so much for your attention, and I am open for any questions.
Thanks, Professor Nikitin. Question, please.
Can I make a question? Can you hear me?
Yes, yes, I can hear you.
Hi, this is Paolo Nepa from the University of Pisa. Hi, Pavel.
Oh, hi, Paolo. Yeah.
Each time I see a presentation from you, I can learn something more. I can better understand how RFID works. Actually, thanks a lot for your presentation. I have a couple of questions for you. First of all, about the smart RFID systems using 2 different frequencies, one for harvesting and the other one for backscattered modulation communication. What is the frequency you are going to use for harvesting, energy harvesting?
That particular example was from IEEE. I think they used 2.4 gigahertz. The idea was that you are putting your tag somewhere where there is Wi-Fi that operates at 2.4 gigahertz. So the tag is always energized through Wi-Fi.
Okay.
So that was an application.
Okay, understand. So because maybe in indoor scenarios you are always having such energy from Wi-Fi. This is the idea, maybe.
Yes, even though Wi-Fi is typically has smaller transmit powers, up to 20 dBm, I think.
And what about green tags or eco tags? Probably you had you hadn't enough time to tell us about tag technology. But nowadays there are a lot of papers. It seems that there is also interest from some companies to produce green tags, like tags on paper, tags realized with conductive ink, and so on. I don't remember the name actually of the company that started producing tags, green tags. Now, sorry, I cannot remember, but probably you have seen those tags. What is your opinion? Does it make any sense to produce green tags?
From the point of view of ecology, it makes sense. The tags that are biodegradable, etc. From the point of view of RF performance, it doesn't make sense. So that center that certifies tags, which is called ARC, for performance on several items like jeans and leather, etc., etc. All of the tags that are certified are non-ecology tags. Basically, they are classical aluminum antenna on a plastic substrate. Because if you think about it, as soon as you substitute aluminum for conductive ink, all of a sudden you have more losses, you have less conductivity. As soon as you substitute thin plastic for paper, same story. So all of a sudden you start losing dBs here and there. So from point of view of performance, it doesn't make sense. But from point of view of ecology, yes. And I don't know which point of view will win.
Okay. Thanks. Thanks again. Thank you very much.
I cannot
Thank you
hear.
very much, Professor Nikitin. No more questions.
Questions?
Yes, спасибо.
Вам спасибо.
Now I invite Professor Chakravarthy from Kettering University, USA.
Hello, can you hear me?
Yes, Professor Chakravarthy.
Yes.
Okay. Let me say whether I can share my screen first to make sure that everything is working before I. Can you see the screen?
Yes.
So you can see the screen, right? My PDF file.
Yes.
Can you see the screen or only the PDF, or you see the whole screen?
Just a minute. What is the problem?
I just want to make sure that you are able to see the presentation file and not the entire
yes,
screen.
Professor Chakravarthy, we see the screen. Thank you. You can start your presentation.
All right. Okay, thank you. First of all, I want to thank Professor Vishnevsky and Professor Gosarov for organizing this wonderful conference. Unfortunately, we couldn't be there because of the COVID situation. And and having said that, I just want to start out by saying, Zdravstvuyte, okay? And now my presentation.
Hello.
Yeah, thank you.
Thank you.
And you can all see the I'm going to move it to a different place here, if you don't mind. Just tell me if something is not correctly showing it. So you can see the whole screen now, right? Do you want me to make it look bigger, or is it okay?
Everything is fine.
Okay. All right. So my presentation is going to be on Q. And all the stuff. So there is hardware component to it, so that you could think of this as the manufacturing. And then you can think about the service component, because all the devices are subject to failures, right? So we always have some kind of an interruption, even when we are making this, conference, virtual conference, or even virtual classes that we all have to go through, unfortunately, with the COVID situation. Then what happens, sometimes the system crashes because of overload or power surge, or you name it, okay? The interruption could occur in many different forms. So with that being said, people always look for quality of service. In fact, the competition is such that it's really a cutthroat. Okay, so what was good yesterday may not be good today, and what is good today may not be good tomorrow. So we got to keep improving everything that we do, a continuous improvement. In fact, I tell my students in my statistics as well as in my operation research classes, if Intel, which made the room size computer into a desktop using their chips, 8086 processors, if they were very happy with what they did, they would have been out of business in no time, because you have to keep developing chips and keep improving it. Okay, now what we were able to see it in an entire computer can be seen on a less capacity USB drive type of flash drive. Okay, so having said that, the same thing applies to stochastic modeling. Okay, so having said that, on a day-to-day basis, we come across items, okay, manufacturing and industry. So how do we use queuing models? Because queues are everywhere, okay? Whether we do on a recreational purposes or we are talking about really modeling to a situation that you want to communicate all the messages coming in a proper way. Even when people Google and do all the other stuff, they have to get this information in a short period of time. And so how do they manage their service providing system? Okay, so through cloud computing and all the other stuff. So how do they do that? Okay, so they're all part of, using queues in some form or the other. Okay, operational research tools, of which queuing system is one particular tool. Okay, all right. So again, quality of service, as I said, is very, very important. So you have to make sure that we can provide quality service, which is not static. Okay, it is going to keep improving it. Okay? So that means we need to develop queuing models that are more practicable, okay, practical and implementable in real life situations. Okay. And I'm not saying that we don't have any models, but we don't have that many models that we need to keep, really improving that. So that is the whole purpose of this general talk, okay? So we need to increase in the literature the number of such implementable solution-based queuing models. Okay? All right. Again, another thing that we have to be very careful about is, especially now, it's more so than ever before, is customers or messages. You can just replace, when I say customers or jobs, with messages or patients, because queues are everywhere. Okay, healthcare system, which is another prime example of a service industry. So they all arrive from different sources. The question is, how do you model the inter-arrival times from sources, even if they are independently generated, unless you assume inter-arrival times are all to be exponential. That is, if you assume Poisson processes, the superimposed processes that are going to be input to your system is not going to be a renewal process anymore. So that means we need to worry about the correlation that is present in the system. Okay? And of course, we also know that the output process, even if you have all input to be renewal processes, the output process need not necessarily be a renewal process. Okay. All right. So there are lots of tools available. Okay, analytical models. See, analytical models, the drawback is that you can only go to certain level. So because of that, we all tend to assume, so that we can present analytical results to a point, the state space doesn't explode exponentially. So we make some assumptions that are good. Okay, I'm not saying, that's not the way to do it. In fact, we do need them, because if you're going to, lean on simulation for modeling, you need to validate the results. Okay, how do you know the simulation is going to produce the right results, right? So we need to have analytical models, but at the same time, we also need to have models that are more practical. Okay, so use simulation as a tool. It is not something that we can look down because, it takes more time, certain times, it takes more time to simulate because you want to get the steady state behavior. And especially when you have a very highly correlated and highly variable processes, then simulation takes more time to get into the steady state. But that's another topic by itself. All right, so the main purpose here is to show how stochastic modeling, specifically queuing, is going to be used in practice and how we can add more to that literature. Okay, so that's a point of this. All right, now very quickly, I know the audience here is very well versed. In fact, I just want to point out the book recently published by Professor Durin, Professor Klimenov, and also Professor Wisniewski is a great addition to the queuing literature, where they talk about a variety of models under correlated flows. Okay, so just bear with me just to make sure that the presentation is complete. I just want to quickly go through that. Now, in the whole idea of the phase step distribution and the Markov-level process developed by Newts in the 70s is to shy away from the exponential Poisson process assumptions, because you could really, I mean, look at this, okay, when reliability, when you talk about wear and tear of, let's say, the batteries or tires or even, mechanical devices, unless you have electronic devices, most, even some of them are really, dependent on the lifetime in the past, not necessarily it's going to be acting like a new one. So in those cases, to use the memoryless property for, again, as I said, the lifetime of a tire in your car, to assume that it's going to be new, having already, put on like 10,000 miles, and it's going to perform like a new one the next 10,000 miles, make no sense. So with that in mind, Newts developed a class of distributions. The beauty of that is it is dense in the class of all non-negative distributions. Okay, so you got the phase step distribution that is defined in discrete time as well as continuous time. So you have a finite state Markov chain with an absorbing state. Okay, and the time until absorption, starting from one of those transient states, is what you're looking at as the phase step distribution. And this includes well-known distributions like, exponential, Erlang, hyper-exponential mixtures, and even in some cases, the infinite mixture subject to the coefficients. The infinite mixture follows the geometry distribution and things like that. Okay, again, these are natural extensions to Poisson processes and gets away from the restricted class of distributions. Okay. Again, all you need is just a simple matrix analysis for implementing the models using phase step distributions. And then there are a lot of, again, this is given for the continuous time, and I think I can skip some of these because of the background the audience has. And so you can find the probability distribution function in terms of the initial probability vector alpha and the t, which is a matrix, square matrix of dimension m, which has the property that the diagonals are negative and dominate the off diagonals, such that at least one row sum is strictly less than 0. Okay. All right. So the examples that correspond to exponential, Erlang, and hyper-exponential are what you see in the next three cases. Again, generalized Erlang is again a special case, and of course hyper-exponential, which is a mixture of several exponentials with different parameters, or it's also a phase step distribution. Again, these are all very simple, and of course, even if you go way back in the 50s and 60s when people did the analysis of Erlang, type of queues, now you can see how explicitly you can get it in many cases, and how using algorithmic solution you can find the solution without really any difficulty. Okay. All right. Now, having done this Poisson process and phase step distribution, then how do we include a correlation into the picture, especially when you're trying to pool the arrivals coming from different parts of the segment, especially now with the supply chain. If you look at any retail stores, okay, they are getting, the logistics is such that they're getting items from various sources, even automobile companies. Okay, those days are gone when they were having only one vendor. Now they have multiple vendors. This is mainly to avoid if there is any problem. Some of them could be nature, like if there is a volcano or if there is a earthquake or storm or whatever it is. If the raw materials are going to be, or even a semi-finished materials, are going to be arriving late because of the vendor having an issue, you can depend on the other vendors. Okay, so if you were to look at those, and again, remember, time is of essence for everybody. Okay, especially if you look at the automobile companies. When they make, on the average, it takes about a minute to make a car because of the demand. They can't afford to wait for the raw materials and shut down the plants. So anyway, to model with all right parameters, you have to use the processes that at least mimic to some extent. Okay. Now, mark point process play an important role. Again, I was mentioning earlier, Professor Dudin and his colleagues' book, and they talk about, in more detail about this very fascinating book. I'm trying to not sell the book because it's selling on its own, but I just want to point out some of the important points they cover. Now, the Markov arrival process itself is a special case of batch Markov arrival process. So what is that? Let me look at the picture first. Again, these are all, the mathematics behind that. And when Newt introduced this, okay, in 1979, the notations were so complex, okay, so that really did not have that, popularity among the audience, and only very few people really understood because of this complicated notation. So in 1990, Newt and a couple of his students, Lucan Tony and Kathleen Meyer, okay, they, found simplified notation. Okay, again, sometime in the literature, people attribute the Markovian arrival process, the simplified notation, to somebody else other than Newt, but actually it is the Newt's one. It's almost like saying, instead of using this particular parameter, I'm going to use a different parameter. But the underlying process, the underlying mechanisms, and the underlying applications are all based on Newt's original paper in 1979. Okay. All right. So they were able to, again, they published this as part of their vacation models using BMAP arrival processes. So what they did was they came up with the following. Excuse me. By the way, is this flickering on your end? Because I see flickering on my screen. So I was just wondering whether the audience can see it without any flickering on the screen. Can somebody respond to me, please?
It flickers only on the top of the slide, but the whole picture is fine.
Okay, so okay, let me see whether I can move it to the other side, because I don't like to have flickering happen. So,
no, the flickering has gone. It's fine now.
Okay, all right. So let's look at this picture here. Thank you, Dmitri. Now let's look at this picture here, okay? So imagine that you have a transient state and you have an observing state where my mouse is pointing, okay? So you start in one of those initial transient states, okay? And let's say that you are in state I. So you stay there for an exponential amount of time with parameter lambda I. At the end of the sojourn in that state, you have one of two possibilities, okay? Either you go to an observing state, okay? In that case, okay, what it means is that you have an arrival to the system. Okay, think of this as a black box. So at the end of the sojourn in state I, okay, you go to an observing state, and at that moment, an arrival occurs, okay, of size, since we're talking about the batch Markov arrival process, you have a batch of size k is greater than or equal to 1. And that is the outcome from that black box saying that, okay, a batch of k customers or k jobs or k messages have arrived to the system for processing. And then immediately at the time, the black box, the internal mechanism governing the arrival process, is such that it's going to start in one of those phases. How does it start? Because you got the absorption occur from state I, that's a key, that's the beauty of this Newton's Markov arrival process, which enables one to capture the correlation, if any, present, okay? So where you're going to start, where, let's say we're talking about M state Markov arrival process underlying Markov chain continuous time. I'm talking about the continuous time. Similar one is therefore discrete time. So because you have to start in one of those M transient states, if you are going to model your state, the probabilities that depend not only on the state from which the absorption occurs, but also on the size of the group that arrive to the system. So you have a bunch of probability density functions, discrete probability density function, Pijks. Now, if you are going to assume that I am not going to worry about from where I got absorbed, but I'm going to start in one of those M transient states randomly using some kind of a probability structure, then you have an arrival process which is going to be independent and ironically distributed one. Okay, so in that way you can specialize this to your phase-step distribution, of course, which includes the Poisson, Erlang, and hyper-exponential, not to mention all other possibilities. Okay. Now the second possibility is that the underlying Markov chain moves into a different transient state. From I it goes to J. So that means the transition occurs, but there is no output to the black box. That means there is no arrival to the system. So the Qij's govern that. Okay. So you got a set of probabilities and the rates. Now, combining these lambdas and the Q's and the P's, you develop a sequence of matrices. That's what we are talking about in the D0, D1, D2, etc. So D0 corresponds to no arrival. So it's only the internal transition within the black box, and all other stuffs are arrivals coming in with a batch of size 1 or more. Okay, there is no limit on how. And the beauty of this, again, the Markovian arrival, the batch Markovian arrival process is in a distributed computer network. Let's say there are k different types of messages arriving. Okay, so from different sources. So you can look at D1, okay, D subscript 1 as the transitions governing to the arrival of type 1 message, D2 type 2 messages, D3 type 3 messages, etc. And then D, let's say capital K, is going to be for the kth message. So that way you can model a variety of scenarios with that. Again, superimposed, finite number of superimposed Markovian arrival process, again a Markovian arrival process. Okay. All right. So with that in mind, you can choose your initial probability vector in a number of ways. Again, for steady state, you don't need to worry about it. Just take alpha to be the invariant probability vector of the generator Q star, which is nothing but sum of all the D's. Remember, the summation dk from 0 to infinity is going to be an irreducible generator. Okay, and now you can define the arrival rate of your jobs coming in or the arrival rate in groups. So the group arrival, that is, you don't have any, if you don't care about the number in each group, you care only about the arrivals of the batches. Okay, that's given by lambda g. So that is the average rate of batches coming in per unit of time. And lambda is the average rate of jobs coming in per unit of time. Okay, so again, the beauty of this is you can multiply, you can choose your D0, D1, D2, etc. in such a way that you want to have a specific arrival rate of batches to the system to be the same. Because when you compare different scenarios, okay, different models, so you want to have a common theme, which is they all have the same arrival rate of batches, then you have to normalize in such a way that they all will have the same arrival rate. However, qualitatively they will be different in that each one will have its own different, correlation structure and variance structure, and you name it. Okay, and of course you can define what the correlation, all this stuff. Again, I'm going to refer to the survey papers as well as Professor Durin's book on it for additional details on that. Now, what I would like to do is, again, these are all part of the specific cases where you can model batch Markov and arrival process to include batch Poisson process, batch PH renewal process, batch Markov modulator, Markov switched Poisson processes. All of these are found applications in many areas, including computer networks. Okay. Now, as I was mentioning, this is the one that talks about the mark point process in more general context. All right. Now, one of the things that is very, very critical and which is not widely seen in the literature is how do you select the parameter of matrices so to mimic? I'm not talking about estimating the parameters. That's a totally different ballgame. Okay, that is still a very interesting problem because of way too many parameters. So when you're talking about underlying processes to have is m by m matrix, then you're talking about how the number of parameters grow, okay, exponentially. So it is a real interesting problem, and even for a 2 by 2 and 3 by 3 and 4 by 4, there are a lot of algorithms proposed by Soren Asmussen and a group of people who have been working on it. Okay, so if anyone is interested, I would be more than happy to give you some references. But anyway, if I had to choose the parameter matrices so that I will be able to run examples, okay, how do I do that? Okay, now even as I said, in the case of simple map, it is not that trivial. Okay, and there are some publications where if you're dealing with a 2 by 2, you can only go to a certain level with regards to the correlation. Okay, so you need to have a variety of those. So how do we do that? Okay, now let me point out again, the more details are given in that reference there. Okay, so what you need to do is really take two processes. One is the Erlang distribution of order k, and then consider an exponential distribution. So this Erlang is of order k with again, this is an ordinary Erlang. It's not a generalized Erlang. So if you take that, then you get lambda 1 is the parameter for that, and this is lambda 2. And there are there are a set of parameters, okay, in this case P1 and P2, so that you really look at the mixture of Erlang and exponential. So as you know, a mixture of exponential, exponential and Erlang is again, the phase-shift distribution. It's again a special case of map. So the D0 matrix is of this type and D1 is of this type. Okay. Now, what is the purpose of this? The purpose of this is with the parameters K, all right, and P1 and P2, okay, the three parameters K, P1, and P2, along with two other parameters, which are lambda 1 and lambda 2. So basically, you got 5 parameters. Okay. Remember, Q1 and Q2 are the complement. So if you know what P1 is, you know what Q1 is, and similarly Q2. So with those 5 parameters, if you really play around and see how you can generate a variety of scenarios, okay? So again, the details are given here. I'm not going to spend, because I know I have only about half an hour or so, so I want to cover a few things in here. So without wasting too much time, again, the details are in the in an upcoming chapter that Professor Vladimir Anisimov is coming out soon, and there is a chapter that talks about this. Anyway, so with that in mind, I would like to show you some key results in here, okay? So if you look at the 3-dimensional picture, again, I'm going to be looking at even a little bit more special cases, namely, I am going to take, okay, basically, I'm going to take P1 and P2 to be the same, okay? And lambda 1 and lambda 2 are such that, okay, I'm going to take lambda 2 proportion to lambda 1. The proportion constant is given by R. R could be, of course, R has to be positive. It could be less than 1, or it could be greater than 1, okay? All right, so with that in mind, if you look at the, again, these are all numbers. I want to show you some picture in there, okay? So basically what you see in this picture is, okay, which is, what is this picture here, okay? So on the z-axis is your correlation coefficient rho as a function of k, the order of the Erlang, and then p, which is the probability, the mixing probabilities, okay? And R is, remember, R is the proportion to the parameter lambda 2, right? So depending on how R looks like, you see how for small values of R, that is when R is less than 1, the values of rho restricted to be anywhere from -0.3 to +0.3, okay? So this tells you that it gives an idea if somebody wants to develop some, for numerical purposes, I want to see what happens if there is a very high correlation in my arrival processes. Okay, let's say the correlation, I need to model something like 0.7. You know that, okay, lambda 2 cannot be less than lambda 1. It has to be much higher, okay? So that's the purpose of this one. So you see that when R is greater than 1, we have a much wider coverage for getting a Markovian arrival process, okay, which will have a much better, much higher correlation that you want to figure this out. All right, now, so this is just to give you an idea. And what I'm going to do is, as you know, the quality of service is very important. So that means we are talking about a system where, let's talk about what do you mean by quality of service. Okay? As we all know, when we go to a grocery store or when we go to a bank, we need to make sure that our time, non-value at a time waiting in the queue is as small as possible. Similarly, in communication applications, when the job's coming in, when the message is coming in, the goal here is to transmit the messages as quickly as possible. Again, this is really very important, even for example, a homeland security. If they're going to have all kinds of data collected to really monitor certain, key things, key places, so they need to send the messages. They need to send the, biometrics or whatever the messages, it has to be transmitted to the analysis station, right? So that means we are talking about not just the average or the standard deviation, but more than that, okay? So again, you will see some interesting results, even in the context of well-known queuing model like MapPH1. And again, these are all going to be useful in real-life application, because if for some reason, and again, I tell my students in the class, how do they find out, for example, Domino's and other pizza delivery, pizza making and pizza delivery, they guarantee like 30-minute delivery to your place. If not, your pizza is going to be free. So how can they guarantee? Because if they are going to take average time to deliver is going to be 45 minutes, if they're going to guarantee 30 minutes, they'll probably go out of business in no time, right? So they have to look at the tail this probability distribution function of the delivery, this service time, right? So that's what we are talking about here, okay? Anyway, very quickly, if I look at the MapPH1, that means I'm going to talk about, again, a simple example, but wealth of information coming out, and that is a point. And then when you go into BMAP-GCQ, obviously, either use some kind of an approximation or use some kind of a restriction on that, or you can rely on assimilation to make it more practical and implementable, okay? All right, so in this situation, defining the state space as given in the bottom of the slide here, so you can define the set of states, which are we call levels, and what you get is really a Kossai birth and death process, QBD process here, and you can, all these results are well known, but I want to really go into the key aspects to that, okay? So again, the stability condition, all this well established, and the rate matrix is a very important one, which is obtained using the matrix quadratic equation. And so once you do all this stuff, again, Guy and Ram, they came up with this quadratic logarithmic reduction algorithm, which really simplifies the computation, as well as reduces the time of computation really significantly, especially in those days when you have a problem with the computing power. But even now, this is an amazing tool to use. All right. Now, again, you can talk about the steady state probability vector, and then you can talk about the getting the tail probabilities. Again, the technique used is by Ozawa's technique. It came in 2006 or so. It's a very interesting and very powerful technique. It's also true for GIMO type of queues too. But anyway, so with this one, you can really use uniformization technique as well as the matrix analytic methods to calculate the time-dependent probabilities, which are the tail probabilities, okay? So we did that, and what we have here is I want to show you the, again, these are all the standard measures, so I don't have to tell what each means and how you calculate and all this stuff. But let's go to the key one here. Okay, so I look at the various probability functions, services, and Erlang exponential and hyperexponential, and calculate various measures for a set of processes which have a negative correlation, positive correlation, and renewal processes. Okay, now let me show you the picture again. You know, the correlation varies anywhere from again, if you look at the previous slide, anywhere from minus 0.78 to plus 0.78. Okay. All right. So if you look at this picture, there are a lot of interesting things show up. Okay. First of all, if you look at the one that we know, which is very well known, is if you look at the middle part of it, okay, where it says REN, the renewal process, the middle part of it is, we all know that as the variation in your service time increases, okay, the mean, I'm sorry, okay, again, okay, I want to point out the legend. Okay, the black circle is the airline services, the white, the round without fill in is the exponential, and the inverted triangle is the airline. So you see that as you know, the variation for airline is much less than that of the hyperexponential. And again, if you look at this in terms of the coefficient of variation, exponential is 1, Erlang is less than 1, and hyperexponential is greater than 1. So we all know that as the variability in your services increases, the mean queue length increases. But the interesting stuff that we notice that is, if you look at the, again, I'm looking at the picture on the left part of the graph here, okay? The 3 graphs. So if you look at the negative variable, so if you look at this particular plot, what is it we see in here? Okay, we see that as the negative correlation increases, okay, that is, as you go from higher, that is negative values to less negative value. Okay, in magnitude it increases this way, but if you look at the the correlation per se, so what we see is that the increase here is noticed only for Erlang services. So when you have a much higher variability in your service times, okay, you see that there is not much of a difference when it comes to using negatively correlated arrivals. However, when you go into the positively correlated arrivals, okay, you see that even for all variability in services, okay, you don't see much of a difference. Here we see that the smaller variability in services sees an impact in your negatively correlated arrivals, whereas positively correlated arrivals, you don't see the impact of your service time distribution. However, the magnitude of, I should say, however, the positive correlation, as the correlation increases, so does your mean Q length. Okay, and that is an important point to notice, that because if you look at one of the average and the standard deviation, you will not be able to, pick up the next set of slides I'm going to talk about. This is just for the average Q length, right? Now, when we go into the tail probability distributions, you will see even more interesting observations in there. Okay, you can see the same thing for the probability a customer has to wait because the server is busy. Okay, so it looks like it appears to increase as the magnitude of the correlation increases. So if you look at the negative correlation part where my mouse is pointing in this region here, as the magnitude increases, that is, you don't care about the sign, so you see an increase in the probability of waiting. Similarly, for the positive correlation, the increase, right? So that's what I mean, but the correlation does indeed play an important role that people should not ignore that. Okay, so this is just for the simple measures like probability of waiting and probability of, and the mean Q length, okay? And so you can look at the aspect for the tail probabilities, and then we will look at the probability distribution function, okay? So with regards to the tail probability, we see that a higher, okay, first of all, we see a very heavy tail for positively correlated arrivals, okay, with regards to the sojourn time in the, that is the time a customer has to spend in the system. Now, the higher variability in services also leads to a heavy tail in your probability. You can see that in your increase in the probabilities. Okay. Now, let's look at the probability distribution function. So you see some kind of a stochastic dominance depending on whether you are dealing with airline services or hyperexponential services. For example, if you look at the airline arrivals, okay, and you see that for all t, okay, the probability distribution is such that for airline arrivals and airline services, it is stochastically less than or equal to hyperexponential arrival and airline services, okay? And similarly, if you look at the airline arrivals and hyperexponential services, okay, that is stochastically dominated by hyperexponential arrivals and hyperexponential services. So the nature of the stochastic dominance depends both on the type of arrivals and the type of services. Now, if you were to look at the correlated ones, okay, you see a different ballgame already. Okay, so there is a cutoff points. Okay, see how these graphs try to cross each other. So there is a point where the stochastic dominance is not for all t, but it depends on the time point. So if one has to implement this in practice, they need to know what type of arrivals they are talking about in order to implement a policy that is useful for the service providers. Okay, so that is the essence of these examples. Okay, all right. Again, the details are in the chapter, and I'll be more than happy to share it as soon as the print version is available. Okay, again, I have to do some kind of injustice to all this more detailed explanation for the simple reason that I have only a few minutes left and I got to cover a few more slides in here, okay? All right, so whatever I talked about is all in the next few slides in here, and I'm going to have all this, mention this. Okay, let me move on to the, again, when you deal with multi-server queue, again, it's very easy to set it up as a QBD process, okay? So you have a modified matrix geometric solution, and you can go through the same thing, but computationally you can do the same thing, but with regards to calculating the tail probabilities and the distribution function, you have to do some kind of an approximation. So what we have decided to do is, let's look at a general context BMAP GC type of queues. So basically what you have here is you have a batch Markovian arrivals coming into the system, which has C servers, and the service times are independent, identically distributed. So we simulated using Arena, a very powerful simulation software. Okay, in some cases we had to simulate 10 million minutes or 10 million units as opposed to 1 million, depending on whether you are dealing with, very highly positively correlated arrivals. Okay. By the way, even for analytical purposes, sometimes you have to, I always run my code when I develop an analytical model. I use Fortran, and I use 10 to the power minus 8 as my, tolerance level for using block Gauss-Seidel, and of course even the logarithmic reduction algorithm where applicable. If I have to exploit the structure of the R matrix, then I use the block Gauss-Seidel, and again, I'm proud to say that worked with a couple of other people who are attending the sessions here, and so we exploit the structure of R matrix to the point that we can cover more examples, more variety of examples. Okay. All right. Now, so again, we always need to validate. Okay. So we validated the model against map MCQ. Okay, so it's very important. Okay, if you don't validate the model, how would you know? This is what I was alluding, at the beginning, that simulation is a good tool, and analytical models are also very important. And where you need to use simulation, you have to make sure that the simulation is well valid, the models are well validated using the results from the analytical models. Okay. All right. Now, in this case, again, these are all the errors. So for the general services, we have also considered a viable to model heavy tails in your service times. Okay. So again, the details are given here, but I would like to go into my picture to point out key things in here. Okay. Another thing I forgot to mention earlier is that we all know busy period is also a very important one from a resource allocation points of view from the management, right? So, waiting time distribution is good from the point of view of the customers, but from the point of view of the service providers, it is very important for them to know how the busy period is, okay? Because if the busy period is not taken into account to allocate the resources, you may either have a situation where the servers may be kept idle, okay? And since you're paying them, and if they're going to be idle, it's not a good idea to do that, okay? So that's where the vacation models and all the others come into the picture, because in vacation model, it's not really a vacation per se. Basically, you are telling the servers, okay, you go and do something else. So as far as this main system is concerned, okay, the server is not available, so the server is really on a break, okay? Of course, you have a natural interruption where the server, the operators, or the transmission unit in the context of computer networks could fail due to a variety of reasons. So if that's the case, how would you model? Because you have to fix the, the failed server or the failed device that is providing you the service capability. Or are you going to bring a backup server? Is the backup server going to serve at the same rate or a lower rate? I mean, that's the beauty of this queuing model. There is a wide variety of scenarios that one can use in real life application, but you have to choose the parameters in such a way that we are shying away from the Poisson exponential assumption to make the models more useful in real life application. So that is the whole, point of my talk here. So especially for people who are listening and who are really upcoming researchers in this area, I mean, there is really a wealth of models available for people to really explore and maybe try to unify in a lot of such models that we are talking about. Anyway, so let me look at this. Okay, so for the batch Markov and arrival process, we consider constant batch size or a Poisson batch size or a geometric batch size, okay? And what are the things that we found, okay? So the key things that we found was the Poisson and geometric distributions for batches appear to be very similar to each other, okay? So again, among all the arrival processes we consider, hyper-exponential, which has a very high variability, okay? No correlation in, the inter-arrival times are because they are all independent, identically distributed for the hyper-exponential case. However, the positively correlated arrival process, which has a much, much lesser variation compared to the hyper-exponential, but as a large correlation, okay? PC means positively correlated. So that has the highest positive correlation in the examples that we considered. So they have very high tail probabilities for the busy period too, okay? So this again points out the significant role, not only by the variability, but also the correlation. Again, one has to remember this, okay? The PC8 has much less variation. Okay, if you look only at the standard deviation, is much less than the hyper-exponential. However, the behavior is that the correlation, the positive one, okay? Also, the ratio of the mean busy period to the mean sojourn time is smaller for services having a higher variability or a higher or a heavy tail like Weibull distribution. Okay, again, the ratio is smallest when the arrival process is the highest positive correlation. Again, why is this important is if the management that provides the service capability, if they have to balance between having more resources to make sure that the customers, the quality of service measured in terms of their waiting time distribution, and to report to the management that, hey, you are wasting too much money in providing the resources, and I see that the fraction of service busy is not that high, that's going to be indicated in your visibility. So that's why the ratio is very important. Okay, and same thing you can, again, as I said, I can't really do justice in 1 hour for all these key concepts that are in play. And again, when you compare those two Weibull distributions, we see very interesting results. The insensitivity to the service time is seen when rho is large, that is when the traffic intensity is large. And of course, when you increase the number of resources, the sensitivity to the type of service is seen only for the two negatively correlated arrivals. So there are a lot of things going on, the interaction between correlated arrivals and the services, okay? And again, these are all the mean busy period that I just alluded. And again, these are all some of the sample observations, how you have a heavy tail distribution for services like Weibull results in the mean visibility to be less than the mean sojourn time. Again, I should point out that in the literature it is known that the mean busy period and the mean waiting time distribution, they don't really have any connection to each other. In other words, you can't say the higher mean waiting time means higher mean busy period and vice versa, okay? So again, I did a simulation study of the busy period, and if anyone is interested to see that, because analytically, as we all know, since 1950s, people have studied this in using very, very complex mathematics. But again, the expressions are known only for very, special cases. And so for more, complicated cases, then one has to rely on some of the tools. And I thought simulation will give you some idea for theoretical development. I think this to be like a two-way, so you use simulation, get an idea to pursue in your analytical results, and then come back to a simulation type of thing. All right, and these are all how you fit the distribution for your busy period. Okay, you see that invariably, a distribution like Weibull plays a significant role in fitting proper distribution for your busy period. All right, in the remaining few minutes, I know I have to leave some time. I just want to mention other types of queuing model, which I just touched upon as I went through, is queues with interruptions. It's very common in communication networks and other areas where, even in a normal bank, I remember when I was going to get some certificate from Department of Motor Vehicles. Okay, what happened was there's only one person who can work on the document preparation, and that server was constantly interrupted by fellow servers. I said, well, this is something interesting because this type of model has not been studied in the past, even though we have a large, huge literature in queuing with interruption. In fact, Professor Krishnamoorthy, I think unfortunately I missed his presentation earlier because I had a class at the time. He has done quite a bit of work, queues with interruption with his students, and there is a survey paper, and you will see that a variety of interruptions occur in real life applications. So again, from the context of service industry, in practice, I was able to use that interruption that occurred to me personally. And so there are a lot of things one can do with queues and in service areas. And of course, group services. Again, if you look at in automotive industries, they have these catalytic converters, as you all know, that is a key part in your car. So that catalytic, especially for gasoline thing, not for electric vehicles. So that has some noble metals like palladium, rhodium. So the substrate is going to be dipped in that solution. So you can do that in group. So again, use with group services. Professor Dudin and I have done quite a few papers on that area way back from 15, 20 years ago. And again, queues with group arrivals and demands useful in inventory and retrial customers. Again, we see this often, okay, when we call somebody, because I have a billing inquiry, so I call them. So what happens is when you call them, the lines are all busy, so you sort of either hang up the phone or you just wait in the line and then you call again. So that is a queues with retrial queues. And queues with crowdsourcing, again, a useful thing in real life applications, because you think about service providers, like for example Walmart. Okay, they started a few years ago, using the customers who are visiting the store to help them to deliver goods in their subdivision. Okay, for example, let's say I go to the store to buy something, and they have a record that there are a few people in my area. They have ordered food, they have ordered some items. They may ask me to go and deliver. Okay, so again. Recently, Professor Dudin and I did a paper which came in the Journal of Operation Research Journal, so Operation Research Society. So you may want to take a look at that. Again, I'll be happy to send a copy of that paper, okay, electronically. All right, so that is exactly what we are talking about. And so again, recently we did a threshold type. Again, in view of the time, I'm just going to make these slides available to the organizers for use. And say it again, please. Hello? Okay. And now, all right, live will speak. That's what I'm saying. I will open up for people to ask questions. Thank you again to the organizers.
Thank you very much, Professor Chakravarthy.
It's my pleasure.
What is the question?
Hi, Krishnamoorthy.
No question. Thank you for very interesting message.
Thank you, Professor Wisniewski.
Thank you.
Hi, Jose.
Okay.
Oh, hi. Varghese, how are you? Jacob Varghese.
Maybe Krishnamurthy did not switch on microphone. Please ask him.
Oh, you didn't use the microphone?
Please.
Joshua, you need to unmute your...
Professor Krishnamoorthy.
Yeah, it is unmuted.
Do you have question?
So, yeah, I'm asking the question. So, what happens when the arrival process and service process, for example, they turn out to be interdependent? I was giving the talk based on that. So that would be rather much more complex, obviously.
Yes, it is going to be complex because you have to take into account the interdependence. Now, can you give an application where it is dependent? For example, if you have a batch service with K customers coming in, the service time may be dependent on the number of customers in the batch. Right.
That would
but
be
if you start with the inter-arrival times.
Yeah, okay. Oh, different groups, among them interdependence. Okay. Yeah, even say several arrival will become extremely complex. But Vishwanath devised a simple computational technique by redefining the Kronecker sum. Instead of the identity matrix, he uses a diagonal matrix with a probability vector as the diagonal entries instead of ones on the diagonal. So he just manipulates like that and things are working very well. So that will be for interdependence. Whereas if you just go for the identity matrix as the diagonal matrix, then that independent case automatically comes in. That's the interesting thing.
Again,
And,
I missed your presentation in the morning. I had a class at the time, but
no problem. No problem. But that his computational tool that turns out to be really interesting. But the interdependence, that theoretical side I was speaking about, and Vishwanath's this computational aspect also just mentioned briefly. That's all. But
okay.
whatever we have talked about, that interdependence will be playing a very crucial role if you just introduce that into it.
Of course. Of course.
The computational complexity, but that can be easily handled by employing Vishwa's technique.
Okay.
That's all my comment. It is rather a comment rather than question.
Hi, Alexander.
Oh,
how are you?
Alexander is also there.
Yes.
So he is not seen.
I'm seeing him now, but he's
I
even I see Professor Krieger. Hello, hello, Ida.
Another question. Do you have? No question. Thank you very much, Professor.
Oh, it is my pleasure. Thank you for giving me the opportunity. Nice to see my friends here.
Thank you.
Professor
Okay.
Krieger, you have a question, No. Okay. Hi, Alexander. I can hear you. You're unmuted. Alexander, you're unmuted.
Yes, I can hear you. I switched on the microphone. Okay, nice to meet you.
Dear college, we have finished the plenary meeting. Many thanks to all the participants. Thank you very much.
Thank you. Thank you.
Thank you.
And we will, it's a good platform to meet people. That's one nice thing about it. No matter where you are, you can see them all.
Okay.
Yeah.
Okay. Thanks.
Thank you very much, Professor Vishnansky.
Thank you, Professor Vishnansky.
Okay. We finished.
Okay. So if people want to chat, that's fine. If you want to do chatting or you want to leave, then we can leave. So, okay, Professor Vishnansky, I'll see you tomorrow then. Okay, thank you all.
No.
Thank you very much. See you.
Bye, Krishnamoorthy. Bye, Joshua.
Bye. Okay. Mm-hmm.